those of you who are here, I shouldn't have said that the test is only on last week's material. But this is where now we will see, it is on. This is where you will see the applications, and there'll be some more coming. Compared to the original proposal, this would be the last of the seminars in that list. I gave Dr. Raghavendra a list of some 7-8 seminars I could add. I could not estimate the time requirement very accurately. It was just some guesswork. So he chose the 3 seminars, including this one now. The other 2 you saw yesterday. But since we have time, I'll add some more seminars. And for the last day, I will add a general discussion on the title of the course. What is radiomics? What is informatics? What is CAD? And how do we, why do we do it? And how do we apply it in practice? And general discussion. So I'll add those files later to the same folder through Dr. Raghavendra. So today's application is detection of architectural distortion in mammograms, continuing the work that I showed in Chapter 8 last week. I showed just the beginning part of that project, where we applied the method to segmented regions of interest containing architectural distortion and a few mammograms containing architectural distortion. Today you will see continuation of that work by 3 more students who got their MSc and PhD from me. So this project turned out to be a fairly big project, concluding our work on mammography and computer-aided diagnosis of breast cancer. And I'll list my collaborators and others later on. The project was in collaboration with the University of Calgary, where I worked, and my students and collaborators in engineering and medicine, radiology in particular, and screen test program, which was called screen test earlier in the 1980s until about 2010 or so. Then they changed the name. But essentially, it's the Alberta program for the early detection of breast cancer. As I mentioned, in a screening program, women in a certain age group are invited, voluntary, to come and get their mammograms taken. In Canada, it is from 40 years to 70. So women are asked to come every 2 years to get mammograms done, 2 per breast, the CC and MLO views. I'm not sure if digital breast tomosynthesis has been incorporated yet into the screening program in Canada, but in some parts of the US, that technique has also been included. And CAD systems have also been included in some screening program. Commercial CAD systems have been around for about 20 years, licensed by the United States FDA. And they are used, but they are used as what is called second opinion. The radiologist has to first interpret the mammograms, record the interpretation, and then look at the output of the CAD system, and then may or may not change the initial diagnosis. It is like if a radiologist has some difficulty or doubt about the current case, the radiologist goes and talks to another radiologist. The same thing, now it's a computer. So there have been many studies that have shown that a radiologist plus CAD is almost the same as a radiologist plus another radiologist. So you can cut some costs if you have a computer to assist a radiologist instead of the films being interpreted by 2 radiologists that was required before. Every case had to be interpreted by a minimum of 2 actual radiologists in a screening program. And then they replaced the second radiologist with a CAD system. And there have been many, many studies to show that this works reasonably well. Now you should note that radiologists are highly efficient if you consider the area under the ROC curve, receiver operating characteristics curve. It is not efficiency, it is a combined measure of how sensitivity varies with specificity. You must have seen ROC curves in communication theory or decision making, pattern classification also. So the area under the ROC curve of most experienced radiologists will be 0.92 or so out of 1. CAD systems may have just about the same, 9.2, 9.3. The radiologists and CAD systems may have similar area under the ROC curve between 0.92 and 9.4, but when you put them together, you go to 0.9596. And what is emphasized is that a CAD system need not duplicate what the radiologist does, or what a radiologist does. If a CAD system can catch what a radiologist may typically miss and help in catching such difficult to detect cases, then there is some benefit. If the CAD system does the same and shows here is this calcification, the radiologist, well, I can see that, I don't need your help. Here is a mass, well, I already saw that. So there has to be some complementary operating processes that will fill the gap and boost the total efficiency. That is where screening comes in. The screening programs are geared for that, to catch cancer as early as possible. So, mammography. Mammography was introduced perhaps in the 70s and 80s. When I went to Canada, to Winnipeg in 1981, mammography was still fairly new. It was there, films were there and images were being taken, but screening mammography started in the early 80s to late 80s. And then this was promoted as a method to catch breast cancer early, but in the systems for mammography in the early stages in the 1980s, the radiation dose was substantial, films were not of good quality, digital detectors came only 20 years later. So women were concerned about the radiation, the effect of radiation, the bad effects of radiation, you know that. It could cause cancer. It could cause other problems. The breast has to be compressed, it's painful. And why go there and experience this pain, and there is this potential danger of radiation. So women were hesitant to go to screening programs. And eventually it changed due to improved imaging techniques, reduced dose, improved efficiency. Previously, the recall rate was more than 1 in 10. 10% of the cases would be sent for additional tests. Because mammography images like this were blurry and fuzzy, and diagnosis was not always completely accurate. So when there is doubt, the person would be sent for additional tests, biopsy and so on. So again, women were afraid or concerned that I go there and then I have to go for additional tests, and then at the end you're told, well, everything is okay. So that kind of a false positive ratio in mammography itself made mammography a bit difficult to accept and for the screening programs to be successful. Now the same thing came later on. Mammography was accepted fine, and then CAD came. And in CAD also we have false positives. Every system will have some false positives. So again the concern was, well, we have a program that's running and women have come in and programs are running well. They need a certain portion of the population to participate in the program in order for it to be effective for the general public. If nobody participates, then the field will not develop any further. So a certain portion of the population should come and get this done. It is screening. Most of them will be normal. Fewer than 10% will have some breast disease, and less than 1% will have breast cancer in a screening program. So for that 1% or 10% of the population, the rest of the population has to come and participate. But due to continued education and information being provided and improved quality, it has improved, certainly. And mammograms don't look like this anymore. This is an old film mammogram. So what are the signs of breast cancer that a radiologist looks for in a screening program? Masses, calcifications, bilateral asymmetry, and architectural distortion. Now we saw these three. We saw architectural distortion a little bit, and it's been shown that this could possibly be a sign of early stages of breast cancer, or the term early can be put in different senses. Early stages of breast cancer or signs of early breast cancer, that terminology varies. Typically, it is a sign before a mass is formed. When a mass is formed, there will be distortion. When calcifications are, there could be some distortion. But that's not what is being considered here. This is without a mass or tumor. And that could possibly lead to something else, or it could just stay just that way. So these are 4 important signs of breast cancer. There could be other manifestations, but these are the major signs. Masses are caused by breast cancer due to what is called the desmoplastic reaction in breast tissue. The density increases locally. The cancer is developing, it takes up more blood supply. A mass is observed as a bright, hyperdense object, hyper meaning more dense, compared to the surroundings. And a mass could be very small, like 1 or 2 millimeters in diameter when it starts, and then it could be fairly big. Calcifications, or what are also called microcalcifications, could be very small. I showed some pictures earlier, but they were zoomed in. If you look at this image, it's very hard to see these calcifications. If you zoom, you can see these bright spots. So a radiologist typically works with some zooming function, or with old films, there would always be a big magnifying glass. And radiologists used to sit in dark rooms with a film viewing box that has, it's a light box on which all the films are mounted. But to catch these, the radiologist would have to scan with a magnifying glass. So perhaps most of you can't see that there without the zooming. And if there is a dense region like this, and if there are calcifications in there, it's even more difficult. Bilateral asymmetry, we saw a few cases. The differences in the overall appearance of one breast with reference to the other with the same view. Both of these are MLO, right and left. And this large density area is not here. Is there some way to overcome that noise? Should I put my microphone somewhere else? This is okay? Okay. Now, architectural distortion. So this seminar and this project, which we started in the year 2000 or so approximately, is about architectural distortion. So in our studies, as the field developed, and I attended a number of these conferences, methods were described to detect calcifications. There were thousands upon thousands of papers, and then masses. Masses are more difficult to detect. The easy things are done first. Calcifications, yeah, you can detect them. Masses, a little bit more difficult, but that's been done also. Asymmetry, not as many papers on asymmetry as calcifications and masses. Architectural distortion, even fewer papers on computer-aided detection or image processing for detection of architectural distortion. So eventually we came to that stage with some understanding as to what it is through presentations by radiologists, pathologists, and so on. They showed slides, they showed mammograms, and some articles were written by the medical specialists. So Dr. Desertel, our colleague from radiology and the screening program, came up with some definitions and patterns that we could understand and develop algorithms to detect those. Otherwise, the definition of architectural distortion is very strange. As I said earlier, it says the architecture of the normal breast is distorted. That doesn't help us. That is what the name says anyway. So it is the third most common mammographic sign of non-palpable breast cancer. That is, breast cancer that cannot be felt by hand, by palpation. The normal architecture of the breast is distorted. That doesn't help us. No definite mass visible. That doesn't help us too. Speculations radiating from a point. That's an important feature or aspect of architectural distortion. You see these lines going in other directions. There could also be focal retraction or distortion, and there could be some concavities at the breast border. But this speculated pattern is considered to be the most important sign. But spicules could exist around malignant tumors too. We saw that. So around the edges of breast tumors, there could be speculations. But here, there is no mass or tumor in the middle. It is radiating from a point. So our algorithm that Fabio Iris, who did his PhD with me, he developed this. First, we said we will extract the orientation field using Gabor filters. The orientation field is the gradient and angle of the strength of fibroglandular tissue versus angle at various angles. Filter and downsample, the original or initial orientation field could be noisy. Orientation field, texture, flow, they're all similar in idea, but how you extract is important. Texture flow, as we defined earlier, is obtained using just gradient operators. Gabor filters will detect oriented components, as we have seen, and I'll show more. Then analyze the orientation field using phase portraits. I mentioned that briefly, I'll show you again. Post-process the phase portrait maps and detect sites of architectural distortion. So in our discussions with the radiologists, we came to the understanding that the direction of the fibroglandular tissue in a local window is important. The magnitude is not so important. The brightness, density, they are not so important. They should be denser than the background. That is, they are white patterns, not black patterns. But that's what we detect using Gabor filters. After that, what is important is the orientation and how the orientation is distributed in a window. We saw Gabor filters. They are the Gaussian, 2D Gaussian with sigma x, sigma y as standard deviation or spread in the 2 dimensions and multiplied with the sinusoid, here cosine. The design parameters that Fabio came up with, we said we are detecting lines or curvilinear structures. These are fibroglandular tissues that may go in a certain direction for a small interval of space, extent of space, and then curve and change direction slowly. So there is a certain thickness of these patterns. How many millimeters? Elongation, how long does it go in a certain direction before the direction changes? Is it just straight forever? Most likely not. And for a certain distance, there will be a certain orientation, and then it changes. Orientation theta at every pixel. So the design parameters for the Gabor filters for this F, the modulating sinusoid frequency is 1 over tau to match the line thickness to the cosine. Sigma x is tau divided by the scale factor. Sigma L is L times sigma x. Sigma y, the spread in one dimension, is L times spread in the other direction. That makes it anisotropic or non-isotropic. So there is some orientation, elongation in a certain direction. If it is isotropic, there is no orientation. And then you rotate with angle theta, whichever angle you want and how many other angles you want. And we went 1 degree, minus 90 to plus 90, or 0 to 180, but we mapped it minus 90 to plus 90, about the horizontal. So there is a certain scale factor to the Gaussian. There is a certain frequency to the modulating function, and then there is rotation, multi-scale, multi-orientation. If you want, you can change L also. And you create a bank of Gabor filters, how many ever you want, for various values of L, theta, and F, or tau. So how many scales do you want? How many values of L? Is it important to change it? Do the results depend on that? So you have to analyze and find out how many angles do you want, how many filters. Do you want 180? Do you want 90? Will 45 be enough? So those are questions of implementation. I showed this. I'm repeating some because I don't have all of you all the time. So, but I'll go through quickly those that have. Okay. Those of the topics I have already discussed, I'll mention briefly. So here is a Gabor function oriented horizontally. Its frequency response is here. Impulse response in xy. Frequency response in u, horizontal frequency, v, vertical frequency. DC in the middle. So it's a bandpass filter oriented in that at 90 degrees in the frequency space or 0 in the image space. If you increase L, it becomes longer, it's stretched, and this becomes thinner. The bandwidth is reduced. Same center frequency. If you make the thickness larger, the filter moves to a lower frequency band. So frequency shift can be achieved by tau. Rotation. If you rotate that, this rotates. It's the same thing. So these are the design parameters, and by changing L, varying L, tau, theta, you get a bank of these filters, how many ever you want, for multi-scale filtering, multi-orientation. So here's an example of some picture, and by using that Gabor filter, we get this output, detects lines approximately here. Fabio did a study and showed that when you have this, it's a bandpass filter. It is not only at that angle, but a small band around that. So a few other details at slightly different orientation will also be caught or passed. So there is a certain bandwidth and angle also for a given filter. If you use that, you get these horizontal pieces of those objects. There will be some noise. There are all these little pieces here and there. They're all caught. If you want to measure the area, threshold this, count the number of pixels, multiply by the pixel size, you get the area of oriented patterns. The leaves are not oriented. Or you may say the leaf is that way and this way, but it's big. It's sort of round. So you're not going to catch those here. We're catching only these stems or whatever you want to call these branches. In the case of a mammogram, here is a part of an image with architectural distortion. You may see some spicules here from the middle. We apply a bank of 180 filters, 1 per degree, and with some tau and L. And these are the angles. The maximum response over the entire bank of filters for every pixel is saved in the magnitude response image, and the angle of that filter that gave the highest response is saved in another array, and the angles are shown here. You can see some spicules corresponding to these lines, but some of these lines are hard to see. There is some noise. So when you filter this, you will get a better display. So we analyze that with phase portraits. As I mentioned earlier, phase portraits are a form of representation of a velocity field. A particle is moving in the 2D space with the velocity vector v, x, y, with the x and y components, and a linear equation is given here, a, x, y plus b. A is a 2 by 2 matrix, b is 2 by 1, this is 2 by 1. So that's the equation. Now, given this field of angles, what are A and B, the 6 values of A and B, that can generate something that is close to this orientation field. Depending on the eigenvalues of this matrix A, you get node, saddle, or spiral patterns. This is assuming that you put a particle here and there is a field indicating the movement of the particle in various directions. But in images, we don't have anything moving. So these lines, these angles are taken to correspond to the Gabor angle output. Okay? Phase portraits are related to a velocity field, but we don't have velocity. We are only looking at the angle of these streamlines, as they're called. But a mammogram has so many pixels and so many different patterns, so you can't just take one orientation field of the whole image and stuff it into phase portrait analysis. So you take a small window. Even for that region of interest, we use a small window. I don't remember the size, 41 by 41 or something like that. So we have a bunch of these angles and find A and B. That will minimize the error between the field given and the field generated by A and B, and put that through some optimization, nonlinear least squares and simulated annealing were the methods used, and find A and B, and you get some parameters. So now we have a parametric representation with a model representing the data here. If it is 40 by 40, it's 1600 values represented by 6 values. And then we translate this and scan the image, and for every pixel we ask the question, what are these two matrices A and B? What are the eigenvalues of A? And depending on the eigenvalues, real eigenvalues of same sign, there are 2 values for the 2 by 2 matrix. It is a node. So at the fixed point given by minus A inverse B of that orientation field given by the model, it says there is something at that point. The window could be here. It could say the focal point, the fixed point is there. Or the window could be here and it could say the focal point is somewhere else, and then we throw it out. It has to be within a certain distance from where the window is in the image. And at that point, there is some convergence. And the window could be here, and it could say the A inverse B is here, and it is a node. So at that point, you increment. Saddle, if eigenvalues are real, of opposite sign. Spiral, if they are complex conjugate eigenvalues. That is spiral, this is saddle. We're not interested in saddle and spiral, but we are just showing that there is some scatter of votes and they can be thrown out. Spiral, there is something, but we're not interested. Architectural distortion doesn't look like spiral. So we focus on the node map, and clearly at this point there is an accumulation of votes. So that itself is sort of proof of the concept that it works. But it's not so easy. When you apply it to a whole mammogram, again the window is there, applied on this top of this field, and you run all over the image, and you create this node map. And this is the node map. This is the area in the MASC database where architectural distortion was identified by a radiologist or whosoever marked the database. The magnitude field, only oriented textures, the density information is thrown away. The DC gain of Gabor filters is 0. But we're not detecting edges, we are detecting oriented structures. And as expected, they should converge towards the nipple, these patterns. You see some overall convergence here. But there are many other places where there could be intersections of multiple lines or edges. So yeah, that's like a speculating pattern. It gave a large value there and something here. So when you have an algorithm, it doesn't look at the image like how we would do. We would discard many details. But the algorithm says, oh, there is a node there, there's a node there, so many others. But what we want is that, and that is where we have a large response. And you can see here that there is a clear speculating pattern in the directions of the Gabor filters, giving the maximum response. And here you see some of these lines intersecting. So the method works, but with false positives. We need additional methods to reject all of these others or suppress them somehow. So we put additional conditions, more and more conditions. A matrix like this has some eigenvalues. The angle between the principal axis is 90 degrees, and the orientation field is like that. It is a node. But do we get such nodes in mammograms? Maybe. But another matrix, this matrix has angle between principal axis 15 degrees, and this is a node mathematically, but architectural distortion won't look like these. If you take this, another matrix, again, real eigenvalues of the same sign, the angle between the principal axis 90 degrees, get that. So we don't want these. The condition number of the matrix is defined as the ratio of the principal values. And these numbers are higher than that number, this is about the limit of architectural distortion in terms of shape. So if the condition matrix of the condition number of this matrix A is more than 3, we say don't bother, don't continue with that. So in Fabio's initial work, there were 19 cases of architectural distortion and 41 normal control mammograms from the MAS database. Small database, but that's all the database has. So we put a condition, the matrix A must be symmetric, node and saddle only. Spiral we can throw out. So if the matrix is not symmetric, we don't even process it. If the condition number is more than 3, we don't process it, reject it. So he got sensitivity of 84% at 4.5 false positives per image. Or you could get higher sensitivity if you allow more false positives, but that's not good. But this, at that time, in the year 2003 or so when he did this was comparable to the sensitivity of detection and false positive rate for masses. And we were able to detect architectural distortion without masses with comparable sensitivity and false positive. I mentioned a few years before that Naga Mudigonda did his PhD on detection of masses. I showed you that, flow field and all that. And his performance measures for the detection of masses was 82% with 2.2 false positives per image. So 2, 4, to double, but same order of magnitude, comparable, but architectural distortion which had been not worked upon earlier as much as for masses. So that was a good result, and he got his PhD for that. And then we said, well, let's make the problem more difficult. The next student came then. Architectural distortion started gaining more attention in the literature in the early 2000s. There were a few papers before that, but not many. And then more and more students got interested in that. But as I said earlier, whatever has been done looks easy. Oh, that's easy, I can understand it. But nobody had done that. So the easy things were done, the next will be more difficult. So we said now, for the next student, we're not going to work with the same database. Take the films before cancer was detected in the mammogram, in the screening program. The radiologist selected cases of what is called screen-detected cancer. A woman has been coming to the program for a number of years. Let's say in the year 2000, cancer was detected. And the radiologist will always go back and look at 2 years before 1998, 2 years before that 96, what was there? Did we miss something? So those previous images are called prior mammograms, prior to detection. And this is screen detected in the sense cancer was detected in the screening program. So we took those, and here is an example. This is where architectural distortion was detected, and this is the mammogram 1 year before. There is something there. But at that time, that was considered to be not significant. Maybe that's why they said come in 1 year instead of 2 years. Or maybe the woman felt something is wrong and came and got another mammogram done. Sometimes the subject or the woman could go somewhere else, or there is something happening, and instead of going to the screening program, she may go to a diagnostic clinic, the hospital, or somewhere else, and then a different procedure is done outside the screening program. Then it is called a case of interval cancer. Between 2 years when the woman is expected to come to the program, she has gone somewhere else and diagnosis is done somewhere else. That information comes to the cancer board and comes to the screening program, and the radiologist will review the previous mammograms as to what happened, what was happening before cancer was detected. So we got such films. As I said, the screening program is extremely tightly controlled for good reason. I'm not allowed inside, and I cannot even touch the folders containing films or anything. And when these images were digitized in our lab using a high-resolution scanner, laser scanner, mounted on an air suspended table, a member from the screening program came, and one of my students sat with her, and they digitized the film, and in the evening she would take them back. and put them in the screening program. So these are some of those images that were digitized. And as I mentioned, preparing the database itself is a lot of work, months of work. Once that is done, if the database is made public, then others can do better work. They can say, well, you only got 90, I'll make it 95. But there is a lot of work before that can happen. So this is the region and the corresponding region marked by the radiologist. So we asked the radiologist, why was this not detected? And what he said is, well, sometimes some signs are indeed detected. And they may say it is not actionable in the sense it's not clear enough, we cannot take any action, so come back in 1 year instead of 2 years, or come back in 6 months. It could be 6 months, I don't know, 96, 97. So they will ask the person to come back and get additional mammograms taken earlier than the typical screening interval. So one of my students, Shomishta Prajna, she did her master's thesis on analyzing these cases, screen-detected cancer cases, by using the node map as before. In Fabio's work, the aim was only to detect this and just say how many false positives, like those. They were also detected, you simply quote the number of false positives. Next, in Shomishta's work, we said we will detect all of these peaks. And at every peak, we will take a window and analyze those windows by further feature analysis, feature extraction analysis, and classify them. We need a training data set, so train a classifier and then classify. So we will allow 20, 30 false positives at the initial stage. Detect how many hour peaks you have and cut, I'll show you that. Cut windows, put them through pattern classification instead of saying I'll only detect one. So that is what Shomishta did with the screen detected cancer cases like these. And interval cancer, I said, is another kind of situation where it is even more difficult in the sense breast cancer was diagnosed outside the screening program in the interval between 2 scheduled screening sessions. So the screening program has old mammograms. But the woman went somewhere else and cancer was diagnosed. That information is not available to us as to the mammogram taken for diagnosis. That is not shared. Only the information that she did develop cancer goes back to the screening program. So the diagnostic mammograms were not available. It is called an interval, just a name here as to what the terminology is. So Dr. Desertel, in the screening program, we went back to the prior mammograms of interval cancer cases, not knowing what the mammogram is on which cancer was detected. And then those images were prepared as a data set for the next student for whom we had to make it more difficult. And this work was done by Shantanu Bonik, who also did the work on the 3D image processing that I showed yesterday. So in Shantanu's work, we had this data set, 106 prior mammograms of 56 individuals diagnosed with breast cancer. These are interval cancer cases. We don't have the mammogram on which cancer was detected, only the previous ones. So the time interval between prior and detection mammograms for 33 cases was an average of 15 months in the range of 1 to 24 months. There were 52 mammographic images of 32 normal individuals, and these were selected to represent the penultimate screening visits at the time of preparation of the database. So what are the normal cases? The person was normal in one screening instant, and we took the one before. So confirmed to be normal in that, and not only at that stage, but also 2 years prior to that. So definitely normal from the screening program. The problem is, these prior mammographic images of women with breast cancer, there is no reference. But Dr. Desertel did a rather difficult task, and regions of interest were marked where he estimated the cancer to have had some signs at that time from the reports from the diagnostic clinic as to where cancer was found. So he had to look at the image, and perhaps the signs were very poor because they were missed by 2 radiologists in the screening program. Or 2 radiologists in the screening program at that time for the interval cancer, these prior mammograms, 2 radiologists had said there is nothing suspicious. And then something happened. How could that happen? Maybe there were some very fuzzy, unclear signs and something developed. Or maybe there were no signs at all and cancer suddenly quickly developed in a few months. So Dr. Desertel marked these regions and said these are where the cancer was indicated to have developed, and these are the suspicious regions related to what could be architectural distortion. So this database is sort of uncertain, but there is something happening there, is the point. And we said there is architectural distortion, and Dr. Desertel said, yes, there is something there. You can see some fibroglandular tissues going in other directions. Normally, they should all be going like that, and they are going. Here, you see some fibroglandular tissues going in other directions. So those are sites of architectural distortion or suspected architectural distortion in prior mammograms of interval cancer cases. So here is one such example. Now it is all prior mammograms of interval cancer. Gabor magnitude. You can see, once you cut this out and Dr. Desertel says it is there, then we say, oh, yeah, I can see it. Especially after Gabor filtering, very clearly there is a scatter of orientation. The orientation field shows that there is a node there in the node map. The full mammogram was processed. I'm just showing a small window of the region marked by the radiologist as suspicious. So then we said, we won't just take that one highest node. We will break the image into as many parts as we can, as the nodes that we can detect. If we can detect 20 nodes, we will take 20 regions. If we detect 30 nodes, we set up to 30. The number 1 node may not always be indicating, the spot indicating architectural distortion, but in this case it is number 1. The highest node is in the region marked by the radiologist. There are a few other nodes. These are the nodes marked up to, I see 26, 27, 29, okay. And 21 is also here. And where is 2? 2 is here, close to the nipple. Perhaps 6 is the nipple. So there are a number of others. We don't know what they are, just cut them. And they are overlapping little windows. And we said, take them all and put them through pattern classification. If you don't want 30, take 10. It's up to you. And these regions were marked as true positive if that region overlapped at least 50% with the region marked by the radiologist. The window size is different. These are squares, 128 square or something. The radiologist marked some rectangle. If they overlap, we said all of these are true positives. If they don't overlap, false positive. So look at true positives and look at false positives. False positives are caused by some ducts and ligaments overlapped. And true positives do have this variation in angle. Sometimes not so clear. False positive due to some edge of the breast or something else coming in. Here we can see some other structure intersecting with fibroglandular tissue, maybe a duct or a vessel, fairly thick. So we call these potential sites of architectural distortion. And then did all of these. Phase portrait analysis gives you one value, the node value magnitude. How strong is the node? How many votes were put there at the center of that window? Fractal analysis, fractal dimension. I'll talk about fractal analysis briefly here, and then I have another seminar on fractals. There will be some repetition between these because I prepared these seminars just as 1.5 hour seminars separately, but some things will be common between them. Analysis of angular spread of power. Now, phase portrait analysis is old. Fractal analysis is new, but not our idea. Analysis of angular spread of power, this is where we have, or Shantanu has done a lot of work. Parallax texture measures for comparison and inclusion in case they work. Loss texture, we discussed the filters used for loss measures of texture energy. So we got a number of features, 80 or so per window, or ROI. And then put them through feature selection, pattern classification, different feature selection and pattern classification methods, different training procedures, classify them as true positive architectural distortion or false positive and throw them away. To derive loss texture features, we applied a transformation, a geometrical transformation. A true positive ROI is shown here, the Gabor magnitude output. You see these fibroglandular tissue patterns at various angles. But the loss texture features are designed to detect what are called ripples and waves. Spots, but we are not interested in spots. Average intensity we don't want. But we wanted to look at the possibility of using loss measures of texture as seen as ripples and waves. But there are no ripples and waves in this pattern. But when you map this by radial or Cartesian to polar transformation, you start seeing ripples. What we expect is from the center of this node, there should be lines at various angles. Sometimes they are not from the center, but at a mathematically exact pattern of speculating radiation will have multiple lines at multiple orientations intersecting at the center. So we expect an angular distribution of those specules. If I do a polar transformation, taking the center of this region, which is the center of a node, as determined by phase portrait analysis, and if I use this as radial distance and then theta, 0 to 160, 360 rather, then these specules will become straight lines. For a given angle, as distance is increased, there is a line that becomes a vertical line. So if there are a number of them, then that looks like a ripple or a wave, but not in the original image. So after geometric transformation of the image and the Gabor magnitude output, we computed the wave detector W phi of loss, ripple detector R phi, L phi intensity doesn't matter, but in Gabor magnitude it shows that pattern. So now you compute the texture energy from these outputs of the loss filters and use them as features, not from the original image. So the geometric transformation is an important step that we introduced. Similar to rubber band stretching transformation of Sahainal and others that I showed earlier, where a ribbon around the mass is transformed to a rectangle. But here this is Cartesian to polar transformation. It is polar, but we are displaying as a rectangle. Sorry about that noise, I don't know what is causing. And then spectral and fractal analysis. We want to get angular distributions of everything. Whatever kind of feature we can detect and relate to architectural distortion, make that a function of angle and get an angular spread. If there are tissues at various angles, then it will be some randomly distributed, maybe uniformly distributed spread of energy versus angle, like a Rose diagram. If there are spicules at all angles, then that will also be spread over multiple angles. But if it is simply normal oriented texture pattern of the breast with all the fibers going in one direction, then the angular distribution will be narrow. So entropy and spread measures can distinguish between those. We can also do this in the frequency domain. So here is a true positive region. Its Fourier spectrum in Cartesian coordinates. In polar coordinates, I showed in texture analysis chapter 7, I showed how to convert this, and now in frequency there is some distribution over theta. So integrate on f for various values of theta, you get the marginal density of s theta. We don't care about variation with f, but in fractal analysis, you integrate over theta and you get the values for different f radial frequency, and that is the radial frequency spectrum. So Cartesian Fourier transform to polar, and from polar the marginals, by integrating along theta and f, you get a function of f, you get a function of theta. If you do only fractal analysis, you do this. If you do only angular distribution, you do this, but there is information in both of them. So this says there is a certain preferred orientation or a few orientations of spicules. And when you take the radial spectrum, radial frequency spectrum, I earlier talked about fractal dimension from Fourier spectra related to fractional Brownian motion in chapter 7. So what you do is plot the radial power spectrum on a log-log plot, log of frequency, log of power spectrum, and it is expected that there will be a portion where it is linear. So to that portion you fit a straight line, get the slope, and from that you get the fractal dimension. Frequency method. You can do this in 1D and 2D also. If there is no linear portion, then it is not a fractal, or if the slope is almost horizontal. But when there is such a slope, the angle of that, the slope gives, not angle, but the slope gives you a measure related to the fractal dimension. So a few examples. A true positive region of interest and its frequency domain spread of energy or power, now rotated to agree with the angle of the image. I mentioned that there is a 90-degree shift between the angle of the pattern in the image domain versus its energy concentration in the frequency domain. Now if you rotate it, then you may find that agrees with this, and there are some horizontal patterns and so on. It's better representation than this. Simply plotting. If you take the Gabor magnitude again, you get this. There are these spicules at these angles. Take the Gabor orientation and do a similar Rose diagram. Coherence, the strength of the oriented patterns. I described coherence earlier. And orientation strength is another measure that we computed. All of these show a certain distribution. But if you take a false positive region of interest, you only have this narrow distribution of power. Compared to this, it is broad. This is narrow. So using the spread measure, we can reject false positives. Of course, there is some overlap. Not all of them will be like this or the other one. So for each ROI, angular histograms or Rose diagrams computed with 60 bins, minus 90 to 89 degrees, from Gabor magnitude response, orientation angle, coherence, orientation strength, what I showed, based on the orientation field angle at each pixel. The entropy is, as you have seen before, now over angle, f theta log f theta, after normalization. Then we got this result in what is called, shown as what is called a free response receiver operating characteristics. In FROC analysis, you plot the sensitivity of detection of architectural distortion. How many points that you marked are actually true positive regions? I could put multiple points within the region marked by the radiologist. Then you just take one. You rank order them. So if you detect, if the second one detects, then the first one is false positive, and then the others are false positives too. So you plot this against number of false positives. How many marks that you put were false? As I said, I can throw 30 marks as I did initially, And if I detect architectural distortion, I get a sensitivity of 100%. But on all the images, I'm throwing 30 marks. So on the normal images also, I'm throwing 30 marks, 30 points. Then my false positive rate will be very high. So I have to reject false positives and try to increase the sensitivity and pull back the number of false positives. That is, take this curve up towards this corner. It should ideally go straight up, give you 1 sensitivity with 0 false positive. And then that remains. So it should be 2 straight lines like that. That doesn't happen in reality. So if you use only node value, we got this 80% at 10 or 11 false positives, the blue one. By using selected features based on stepwise logistic regression, the Bayesian classifier, and the leave one image out, there are up to 30 ROIs per image, and so many images that I mentioned earlier. But when you train, you are expected to leave the current sample being classified out. But the ROIs belonging to the same image may be related somehow to this ROI that you are classifying. So you say, I'll take away that entire image. All the ROIs of that image should be left out of the training procedure. Or you may say, leave one patient out. All images from that patient should be left out of the training set. Train your classifier and then test with the current case. So there are different leave one out, leave one what out. So then, by using a neural network, there we got this black line, and using a Bayesian classifier, we got this red line. So now we got 80% at less than 5, or 5.8, somewhere there, 80% and that. Or 90% if you take that, at 8.1 false positives per image. So that was one stage of the work. How many pages I have? Do you want me to stop here or let me finish this?
How much time it takes?
How much time? I have 15 more pages, 15 minutes. You want to stop?
We'll come back.
Okay, let me finish this. Okay, this page, not the whole thing. Okay, this is one stage of the work. And then, okay, we'll come to that later. This is Shantanu's work. Okay? We saw the works of some of my students. That's good, right? You can hear me at the back. Starting from Fabio Iris, and then Shobmishta Pragna, and then Shantanu Bonik. They did their projects. And then this work was done by Jayashree Chakrabarti, who came from IIT Kharagpur to do part of her PhD work with me. We discussed again with Dr. Desatel, and the question was, we were taking all these regions of interest at various positions within the mammogram, detected using node analysis, and then we were treating them all equally in terms of potential regions of architectural distortion. And we were computing spreads of angular distribution. And then we asked the radiologist, are all these equally likely? Are there any properties that are different depending on the position? And he said, yes, of course. Depending on the position of where you are in the breast, the oriented pattern will have a different orientation, normally. So in the normal breast, tissues converge towards the nipple, as I mentioned a few times. And that's because the milk ducts take milk that way towards the nipple, and all the supporting structures are around these structures to support them and hold them together. So the overall texture of a mammogram is expected to have oriented texture this way. So Jayashree drew this diagram based on other pictures we had seen in the literature. And then obviously if you have a region of interest here, it should be having texture oriented that way. If it is here, it should be oriented that way. So we said, okay, let's take that into account in the analysis of regions of interest and detection of architectural distortion. So the main idea is these are what we call the loci of breast tissue, expected. So to draw these lines, we need some reference points, landmarking. I talked about landmarking of CT images where we encountered ribs, spinal canal, hips, and so on, hip bones or the pelvic bone. In a mammogram, if it is an MLO, medial lateral oblique view, there will be the pectoral muscle. Mostly straight line. If you can fit an approximate straight line, that forms a reference to the chest wall. And the skin air boundary or the breast boundary needs to be detected. These are important references for these loci or loci, as you want to call it, plural of locus. And you need the nipple also to be detected. And there are many algorithms or procedures in the literature. I have not talked about detection of the nipple. We have some methods based on the Huff and Radon transform to find the point of convergence and a point on the skin boundary or near the skin boundary. That's in the new edition of the book, but I don't have a presentation on that material. But let's say you have a procedure to detect the edge of the pectoral muscle and the breast boundary and the nipple. And with that, we can form the expected loci. So these are the breast boundary approximated by fifth order and second order polynomials. The nipple is also detected and marked. A straight line approximation to the pectoral muscle is marked. Now the pectoral muscle is going like that, so it's not a very good approximation. But all we want is this line as a reference to the chest wall, from the chest wall to the nipple. So the breast boundary is broken into two parts, possibly three parts if there is a little part here. But we fit these contours to just get an approximate or smooth representation. And then we draw a similar contour by interpolation from the top edge, which is in the pectoral muscle, to the nipple, and this is derived from that contour. In the case of MLO, the chest wall is assumed to be this edge of the image. The upper and lower parts of the breast boundary are approximated by second order polynomials. This is fifth order, the others are second order polynomials. The nipple is there, and perpendicular to the chest wall, assumed to be here, is drawn, and that's another reference line. Based on these, the images are broken into regions marked as R1 to R7. In some images you may not have R4 and R7. So what are these expected loci of breast tissue? And here again Dr. Desertel told us the breast boundary is related to these contours. So knowing the breast boundary, you should be able to extrapolate or interpolate, as you wish to call it, and get the other contours for every pixel within the mammogram in these regions. For that, the images were broken into these regions marked as R1 to R7. And there are some different procedures for these as to how to interpolate, but they're all interpolation, so I won't go into the details. If you go to Jayashree's papers with me, you will find the exact procedure. So essentially, here, using this upper part of the breast boundary and the lower part, and drawing some limits, there is a limit here from the top left corner to the nipple, which is derived using the outer breast boundary, and in between these are all interpolated versions of those contours. Similarly here, these are interpolated versions, and you get these contours for all pixels in the mammogram. I'm showing only a few of these contours. Similarly for the craniocaudal or CC view. So landmarking is required first, and the breast boundary itself approximated by simpler curves. Those curves are used to interpolate and get the other curves, which are taken to represent the expected orientation of breast tissue at every pixel in the mammogram. So here, breast tissue is expected to be oriented that way, and here this way, and there that way. We have seen such patterns. It doesn't happen always at every location. So this is a model. Now, if there is architectural distortion here, then there will be spicules going this way and that way, and which are every other way. But we expect the orientation to be like this. And if your window is only this much, all lines should be oriented like that. Or the orientation in between obtained by interpolation for every pixel. So then ask for the deviation. Using Gabor filters, we have computed for the image the orientation field at every pixel. This says, according to our model of the breast, the orientation should be like that in the window. What is the difference between the two? If there is disagreement or lack of coherence, then there is some suspicious structure. So mark all the suspicious areas like before using node map analysis, and then do pattern classification, trained pattern classification. The rest of the story is the same. So we compute divergence. Mn is the Gabor magnitude response. Theta Mn is the Gabor angle at pixel Mn. Phi ij is the expected orientation of breast tissue at that location, and do that. If the computed angle agrees with the model, the value is close to 0, cos 0 is 1, magnitude is high, so it will be high, normalized with respect to the Gabor magnitude. And this is coherence, they are agreeing. Take 1 minus that for disagreement, lack of coherence. It worked somewhat similar to what we had for coherence. So here is the original image. That's the point of, that's the region marked by the radiologist as architectural distortion. You see some other angles. And Gabor magnitude, Gabor angle, and divergence map. And we see a large one, but there are so many other large values. That's okay. There are many places where the angles don't agree exactly. This is the thresholded map. We can remove some points. Still there is a large value. There is a large value there. So apply this and break the image into parts. And take all these windows up to 30. We have 30 in this case. And put them through. And here, what is that? I think number 5. Number 5 is in the window marked by the radiologist. Not number 1 in this case. Number 1 is somewhere else. So number 5 is there, that's fine. So now put them all through pattern classification as before. If we just look at this, the area under the ROC curve is 0.6, which is not good. 0.5 is random. 0.6 is a little better than random. Many of the heraldic features, if you were to look at them individually, they give you no more than 0.6, 0.65 area under the ROC curve in many of our pattern classification experiments. So individually, one feature will not give you 0.8 or 0.9. Not even, if you get 0.7, you're lucky. That's a good feature. So you have to put many of them together. And as long as they are complementary, then when you put them together through feature selection, then your area under the ROC curve will go up to maybe 0.8, 0.9 if you have a good set of features. So this is one feature. FROC gave 80% at 9.5 false positives, like before, using just this. So which is not bad as a starting point. Then for each of those regions that have been cut, do further pattern analysis. We computed some more measures of specularity and angular dispersion caused by architectural distortion. One of them is called divergence of specules. So if you take one of these regions marked, those square regions marked on the image as suspicious regions, if there are specules, this is the center of the window. If there are spicules, they're expected to be like that. So you find the angle using polar coordinates, alpha 1 and so on. And this is for a pixel in this window at angle alpha 1, if there is a spicule, then if there is a large value of the magnitude, then if it agrees with the angle given by the model, then it is a spicule. So do that for all of these pixels. So what do we have? Mij, the Gabor magnitude or coherence value, times cos of theta ij minus alpha ij. Theta ij is the Gabor angle, alpha ij is the angle of a pixel in the range given by this illustration. So if the Gabor angle agrees with the angle according to this mapping, and if the magnitude, Gabor magnitude is high, this is based on Gabor magnitude, not the expected contours, over a window, then this is an index of divergence of spicules, we called it. So there are many spicules. And like that we defined radial and angle weighted differences. So we defined alpha 1 to alpha 4 to go 0 to 360, and R1, all these points are with distance R, pixels with similar attributes at comparable radial distances or angles make small contributions to RWD or AWD. So these are measures of differences. If you have a spicule, they should be the same value or strong values along a given angle and a given radius, for various radius values for a given angle. There should be a spicule like that. Then for various values of R for a given angle, there should be high correlation. So like this we defined a few more features. The basic idea is to characterize spicules in that window using magnitude and angle response detected by our methods. So we put all of these features. In the end we got some 84 features, I think. Something will come up later. So the FROC curve, using only the peak values, I said 0.8 at 9 point something, 0.8 and close to 10 there. And you want to push this curve up here to this corner. And with selected features, all features gave the blue line, selected features gave a little better response. So feature selection is important. The difference is not much in this case, but it is important. So performance with 2 views per breast. Then we combined the information in 2 views, because 2 views are taken, mediolateral and craniocaudal. And these are the regions marked by the radiologists in red. These are the top 5 or 6? 5. Top 5 ranked regions obtained by this method. So number 1 is here. Number 2 is there. Number 1 here went somewhere else. So the others we don't care. After you rank order, then you still go through ROC analysis, FROC, and then say how many of these are number 1 and 2 and so on. You could do that, or give the sensitivity against false positive rate. So we got 86 features. Speculation features, we defined 12 of them. These are our measures. Harrelson loss texture features, fractal dimension 25. Angular spread and entropy, I described those. Our own design, 15 features. Now, Jayashree also did another project where we said there should be some agreement of angle also in a small window of analysis. So just like you do gray level co-occurrence matrix using Haralick's statistical measures, we said we will do angle co-occurrence. So we asked the question, if the angle at this point is this, what are the angles of the neighboring pixels using Gabor output? They should all be similar if there is coherent orientation. It's like coherence. If they are scattered, then the angle co-occurrence matrix will be scattered. If they're having similar orientation, we get large values along the diagonal, similar to grayscale, gray level co-occurrence matrix, but angle co-occurrence. Angle data will be obtained for every pixel using Gabor filters. So we computed statistical measures of angular dispersion. Now we will view it as dispersion instead of just co-occurrence of similar values. And we use 6 of those and 28 measures of Haralick's measures with angle coherence matrices. We computed 2 of them, 14 times 2. So these Haralick's measures are using gray level values, gray level co-occurrence. These use angle co-occurrence. And then some more measures of angular dispersion and correlation using those Rose diagrams. And we put them all, 86 of them, through feature selection with stepwise logistic regression, and then different classifiers, and the Bayesian gave the best result with leave one patient out. All the mammograms of that person will be taken out during training and then tested on all those images of that subject or patient. So we got 80% at 3.7 false positives per image, which is better than what I had mentioned earlier. And again, comparable to the results reported in the literature at that time for detection of masses. So we have pushed the potential accuracy of detection of architectural distortion close to that of detection of masses when that was a major topic of research. So to conclude this work, Fabio did his PhD, Shantanu did his PhD, Sharmista did her master's, and Jayashree did a part of her PhD on this. So all of that for this project, we made this claim and said our methods could detect or detected with a certain database breast cancer 15 months ahead of the time of clinical diagnosis. That is, these are prior mammograms. On the average, the time difference between the prior mammogram and when cancer was detected was 15 months. And that's when cancer was detected by a radiologist. So if we had access to the prior mammograms at that time, 15 months before cancer was diagnosed for these subjects, we would have detected that with 80% sensitivity and fewer than 4 false positive per patient here, not per image. So 2 images per breast. So that was a substantial result, and Shantanu won an award for his paper in IEEE Transactions on Medical Imaging from the Canadian Cancer Society. So as I said earlier, when Hounsfield won, Hounsfield being an engineer and Cormack being a mathematician, they won the Nobel Prize for medicine. That was big. Oh, engineers are coming into medicine now. And we were happy that Shantanu was able to get this Best Paper Award from the Canadian Cancer Society as an engineer. So a number of grants we obtained. Shastri Indo-Canadian Institute, after our earlier Prime Minister Lal Bahadur Shastri, there is an Indo-Canadian institute that gave some grants for collaboration between IIT Kharagpur and my team in Calgary. 2 students from there came and worked with me. Ashish Dhara also came and did a part of his PhD project. It's not in this seminar. And a number of others gave some grants. Dr. Desato is my collaborator from the screening program. Dr. Mukhopadhyay from IIT Kharagpur, Naga Mudigonda Hilary Alto, Fabio Arias, Shantanu Bane, Shomishta Pragna, husband, wife, and Jayashree Chakraborty from IIT Kharagpur worked on this project. So there's a lot of work, as you can see. Once it is done, it's obvious. So if you go back to the beginning of this work, we had no clue as to how to do this, and there was not much in the literature on this. So over about 10, 12 years, this work was done. All of this that you have seen so far on architectural distortion. Okay, that's the end of this seminar. We will have one more on fractals today, but before that, do you have any questions? Yeah.
Kind of word of appreciation here, because most of whatever we do for a CAD kind of a diagnosis, what happens is once the cancer is there, detection is very easy for even machine learning or deep learning kind of methods. But detecting the early signs is more important. That's what the research is like. So we have to pay attention there while we as researchers here. So I think I'm astonished in like, okay, the computer can detect before the radiologist
No. Okay. We have to be careful there. We have to be careful there. A very famous computer scientist from Canada said, computers will replace radiologists. Radiology is dead. And then many students did not go to radiology in Brazil. My collaborator, I mentioned Dr. Marcelo. He said students are not coming to radiology because this famous computer scientist said, oh, AI will take over. No, AI will not take over anything. Computers will not take over everything. They may take over, because we should still do 2 times 3 is 6 or whatever multiplication at some checkouts in stores. Sometimes it so happens that if the power goes down or if the checkout is not working, then they have to shut down the whole store. Previously, when I was a kid, we would go shopping and the guy would say half kg of this, 10 grams of that, 50 grams of that, and he would just rattle off the numbers and he would say your bill is so many rupees, and he wouldn't even write, or he would just come up with the number. Sometimes he would scribble. He did all that mentally, and then, but nowadays it is difficult. About 2 months ago, the Calgary Public Library system, computer system was hacked, and they had to shut down. It's a digital library. So they said they shut down the whole library for a few days. There was a security concern, yes, but because of hacking of their computer system, they shut down the whole library. Libraries have nothing in them. Even at the university, the libraries are empty, hollow shells. They are ghostly or ghastly buildings. There are no books there. This library has books. What's the problem in telling you want this book? Take it or sit here and read it. They shut the whole library. And then after a few days, they opened, they said, no digital access, only paper books. At the University of Calgary, there is a huge library building, and I walked around, it's all empty. Students are sitting there, there's a coffee shop, drinking coffee and doing something on the computer. Okay, information can be accessed. But all the books have gone away into long-term storage somewhere outside the city. And in the library, there are a few books, but old books that are, in a way, it is efficient management, I should also agree. That those that are not used are kept somewhere else. And when you ask for that, they will bring it back and give it to you. I can also get books from wherever in Canada, interlibrary loan. But libraries have changed quite a bit. But to depend completely on the computer system and say, I cannot give you a book because my computer is down, sounds a little strange. So complete dependence on computers is difficult, could cause problems. But coming back to your point, yes, we have shown that by appropriate design of computational procedures, it is possible to detect cancer before radiologists could detect them. But that doesn't mean my computer is better than the radiologist. In fact, all of this was developed in consultation with the radiologist, and the radiologist gave us these ideas. by drawing pictures and explaining. But how to capture that into equations is what matters for us as computer scientists and engineers. Somebody else may interpret it in a different way and build other types of tools for the same purpose. Like for breast cancer screening, there was some news reports maybe 20 years ago that instead of taking mammograms, send a sample of your hair and they will do some tests and some biomarkers. And didn't go further. Breast cancer screening by mammography is still there. But it could be augmented with other tests. So instead of drawing blood, maybe a hair sample will do. But all of those need time to develop further. So my last seminar, I'm still preparing the notes for that. Like a PowerPoint I'm preparing for the last day. I'll talk about all of these as to where this is going, like what is radiomics and informatics, and I didn't have that. I looked at the title and said, oh, I should talk about those things. So I'm putting some of these notions together. I'll give you some thoughts about that later as to how these can be done, how these should be done, and where credit should be given. Any other questions or comments?
I have a question. When we cooperate with the radiologist, their way of approach for a modality is different. They use PACS and DICOM. And what we use is somewhat like AI. So how are we supposed to integrate both? Like you showed me an image in page number 17, slide number 17, where we saw the overlap. If the node which I have marked overlaps with the other radiologist, we say that it is fine. Otherwise, if it is not overlapping, it is not good. So how do you say that the radiologist will be correct, or the one we did not make the error is where?
There are a few different things you mentioned. PACS and DICOM have nothing to do with image analysis. PACS is picture archival and communication system to display images and transmit and store, and so that is different. DICOM is a standard that says what kind of header should be there, what kind of information should be in the header about the patient, the imaging modality parameters, and then how the image pixels or voxels should be stored. So they are just communication and archival system standards and systems. So from that system, you take your pictures out, the radiologist will view on a monitor, and we get the digitized images and we do the image processing. So that is one. AI has nothing to do with, I don't want to use AI. CAD has nothing to do with PACS and DICOM. They are just tools to facilitate the operation of the diagnostic enterprise, computer or radiologist. How do you say the radiologist marked it in the right place? That is trust and faith. The radiologist is the domain expert. And you and I can't question because we are not trained. We don't know that. So we take that, and the computer algorithms can detect most of them. Yes, we can see that. It is working. Sometimes they fail. And we have asked Dr. Desertel, well, why is it failing here? This tumor doesn't have speculations. He has a nice sense of humor. He said that patient or this tumor did not read the textbook. So they don't behave as textbook definitions. In biological systems, various other things happen in terms of variability being larger. But regardless, we have to take the domain experts' input or opinion as being valid. I cannot say, and I will not say, that my result is more accurate than that marked by the radiologist. There is no argument to support that. As I said, you can get it done by multiple radiologists, but instead of having multiple, it is better to have a consensus of the multiple inputs from multiple medical specialists. That has been done in some studies. So, did that answer your question? Okay. But I would not want to say these will replace the radiologists ever. That's not the idea here.
Anyway, there will be radiologists, they give input to this one and we build kind of a, what do you call it, expert system or something like
true,
that.
true.
That gives some results. The common man is able to see the results of that. He has his own interpretation of that. Before we go into the doctor, we see the Google and what is this tablet, what are the side effects and all. This is the generation of that one. We go and recommend the doctors that you give me this.
Yeah, that's okay. I mean, you should also be informed. When we go to the doctor, we should be informed. You don't want the doctor to spend half an hour explaining to you what is this. And sometimes, in fact, my family physician, when I ask questions, he will go to Google or he will go to NIH or Mayo Clinic or Cleveland Clinic Foundation, all these things. And then he will print it out and give it to me. And sometimes he says, well, you go and Google yourself. He knows what I do. So for me, he will say, but for somebody else, he may not say that. He may actually sit and explain. But if you are prepared, then you should be able to ask questions and understand the response. So when you go to a medical expert, then it will be good to have some knowledge. And there will be cases where we know nothing. Something happens and I go and say, there is this and please help. And whatever my doctor gives, I take that. If I want to read more, yes, now we have Mayo Clinic, Cleveland Clinic Foundation and many others, NIH. We go and read. But I can't do self-medication. Here you can go to the drugstore and say, I want this. In Canada, you cannot. There are these Tylenol and other things over the counter. You can go and buy cough tablets and so on. But if you want a specific prescription drug, you must have a prescription. Here also it says by medical prescription only, but they just give. You go and ask, they give it. That should not be the case. So all the files up to now are available on is it a Google Drive or something? Where have you? Google Drive that Dr. Raghavendra has prepared for you. I'll be putting four more files there, PDF files. The last one is still, I'm working on that. When ready, I'll put them and please download those later on, including this one. This is not yet there. You will get all of these PDF files. We have used fractals in some of our research projects. I talked about fractal dimension computed from the frequency domain using the radial frequency past spectral density. We did some fractal analysis of knee joint vibration signals. Then I thought it would be nice to put a seminar together as a general information seminar on fractals. What are fractals? What do they look like in biomedical signals and images? And how can we quantify or characterize the fractal nature of signals and images? I mentioned this crest or logo of the university. It's not a logo, it's called a crest. This is the new version for digital scalability and all that. So note the standardization of color, and note also the color of the horn of this bull. I mentioned, note that the books are empty. That's the old one. So there was the books had some scribbles. There's no text. Why is that not moving?
This plus zoom is there.
I'm trying to, okay, come down. No, not that much there. Okay. So previously the book had something, this flower also had something. There was the motto of the university, I shall lift up my eyes. And it was translated to eyes high. And that's in Gaelic language from Scotland, I think. The name Calgary comes from Scotland. And the bull also has some hairstyle. And But the bull had a red horn. So red is, it looked like as though it did something. They changed the color of that. So sensitivity of the public and designers has changed. I think I told you, or maybe we were talking, some 20 years ago we were told not to use red pens in marking exams. I told it's offensive. So previously there was only blue and black, or blue-black, and then came green. My father used to use green always, and then came red. And now you have the whole spectrum, pink and purple and mauve, and so nicer colors. But that changed. So what are fractals? I showed you this picture of a fern leaf. I plucked it from the garden. I don't think my wife was happy that I plucked such a big piece from her garden. It shows the fractal nature. One of the definitions is self-similarity at multiple scales. The same pattern occurs. Self-similar, like the same thing. So here we have a certain pattern of arrangement of leaves or subunits. Take each subunit, it looks like the same thing with the same type of arrangement of the sub-subunit. But if I take this and zoom, you can see some structure, but they're not as separated. And if I take one of those little things, then it's lost. It's a physical thing. To make these patterns, you need the physical substance of that leaf. So there is a limit to that. As I mentioned earlier, if in computer-generated fractals, it keeps on flashing and zooming in and creating the same patterns, but that is not true in the sense it is simulated again and again and again. The same thing is projected to you, looks like it is coming from somewhere, but if you zoom in, the detail is lost after maybe 2-3 scales. What do we see in images? Macrolobulated versus microlobulated contours of tumors. That is self-similarity. Nested patterns are complexity of some kind. Smooth versus rough contours, convex versus spiculated contours, geometric versus space-filling curves. These are some kind of nested complexity. So these are two types or two views of fractals. Not always cauliflower, but cauliflower is a nice example. So I took a cauliflower from our kitchen, and if you take individual flowers out, they look like the whole cauliflower if you zoom. So I took one of those, I don't know which one, and it is that. If I zoom this, it looked like the whole cauliflower. I took one of those and I zoomed that, sort of another cauliflower, but there is a limit. If I zoom this, it's just something. If I break it further, then I can't take any picture. You put it in a sub-G and eat it. So there is a limit to this in a physical image, a physical object rather. Now, given a fixed image of 1,000 by 1,000 pixels, let's say, you want to downsample it to see what happens at some other scale. If you zoom in, then cut it to 512 by 512 and so on. Go to smaller and smaller scale. But after maybe 100 by 100, anything smaller, there is not enough number of pixels there to form the pattern that you want to see. So there is a limit in a given discretized image or in a given physical object. There are limits to how many scales of this repetition of pattern can exist. So a few examples of fractals in the human body: the tree pattern of the bronchial tubes in the lungs, branching networks of blood vessels in the body, in particular kidneys, the His-Purkinje conducting system in the ventricles of the heart. You know that the heart has an electrical conduction system, like a wiring system of its own. So from the sinoatrial node, there is a bundle of conducting fibers going to the atrioventricular node. And from the atrioventricular node, there are two branches called the bundle branches. And then when they go to the bottom of the heart, they suddenly branch into numerous sub branches. And that is called the His-Purkinje conducting system. So that branching pattern for rapid stimulation of the ventricles from the bottom up, that is triggered by this network, which is similar to all these branching patterns. The convoluting pattern of the folds of the brain. Convolution here means convolved with itself, folded with itself. Convolution is, in English, it would be taken to mean folding. In mathematics, in image processing, it is the other operation, but there also you take it and sort of, not exactly folding, but it's called convolution there. Here it is interpreted as a folding pattern. So there are similar blobs like a cauliflower. Fractal dimension was defined by Benoit Mandelbrot in 1967, and he came up with this notion of self-similarity and fractal dimension. So one of his famous sayings, it's not here, he said, mountains are not triangles and clouds are not spheres. So they are more complex patterns. Overall, they're like that. But then you add details, you will see finer and finer details. You will get a PDF file of this later. So fractal dimension quantifies complexity as a ratio of the change in detail to change in scale of your measurement or viewing of the object, or of the substance in the object or the pattern. For geometric shapes, fractal dimension is equal to Euclidean or topological dimension, 1 for 1D lines, 2 for 2D surfaces, 3 for 3D volumes. So this is for geometric patterns. Straight line is 1. But if you draw a curve, some wavy pattern, that's not a straight line. It is something between 1 and 2. 2 for a square. This is a flat rectangle. But then if it has some variations in gray level or some pattern, then it's more than 2. 3 for 3D volumes, but if that has some roughness like a cloud, it'll be more than 3, the fractal dimension. So for fractals, the theoretical fractal dimension is greater than its topological or Euclidean dimension. Some basic patterns that are well known in fractals, the Cantor bar, the first iteration, 1 line. Then you break it into 3 parts, equal 3 parts, and take 1 out. And iterate. It's an iterative process. So take this, break into 3 parts, equal, take 1 part, the middle part out, and keep doing. So this is known as the Cantor bar. It's a fractal of some kind because of iterative patterns. Each one is a line, and there is a certain rule that the middle 1/3 is left blank. The middle 1/3 is left blank. And there is a blank portion here. And it goes on. The Koch curve is another, where you start with a straight line, break into parts, take the middle third and cut that in half and make a triangle there. And then take this, do the same thing. Cut in 3 parts, put a triangle in the middle, equilateral triangle. And for all of these. And keep repeating. So I try to make 2-dimensional patterns similar to that, but on a grid in a graphics tool. So some of these are not perfect because I can't make angles, lines at all angles. So angle placement, I encountered some limitations in the very simple TGIF graphics tool that I used. You may have better tools and you may get a better result here. So there is this Koch snowflake where you do the same thing, start with a triangle and break this and make another triangle and break this and put another triangle and keep doing that. So there is self-similarity at multiple scales. Triangles, 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 big, medium, small, 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 and so on. But there is a rule as to how they are placed. There is some inaccuracy there because of the graphics package on a discrete grid. But that shows what the snowflake is. So I said, well, let me do that with circles. That's done with triangles. So what about macrolobulated versus microlobulated masses? So start with a circle and break that into thirds and draw circles. These are all circles, but the inside is blocked out. They're all black circles. So they overlap here. So I'm interested only in the contour. So no lobules. Now there are 6 lobules. I wanted to do 3, but I don't know why I didn't put it. the first stage is 3, then 6. And take each of these and make smaller circles and stick on there. The placement rule is the same as to how these are placed. So on these now I put 3 more circles and so on. So again, there are some inaccuracies due to the discrete grid. So we could call this as a benign mass. This is a macro-lobulated, perhaps this will be smoothed out. In reality, it won't be so sharp. It will be perhaps something like that here. And then micro-lobulated. If you do again and again, the lobules become smaller and smaller. So benign to malignant transition. And that is shape complexity of some kind, as we have seen in real mammographic mass contours I showed earlier in chapter 7. There is another pattern called the Sierpinski triangle. There is some placement rule again. You keep breaking and you get more complex pattern. There is another measure of complexity called lacunarity that becomes evident here. Fractal dimension is based on what is present, pixels that are having a value 1 or whatever. Lacunarity is based on holes, what is not there. So you quantify the holes or absence of material. In a ligament, if there are tissue, collagen fiber tissues, that is fractal dimension. If you analyze the gaps between them, that is called lacunarity. And there are measures of lacunarity that can complement fractal dimension. So here you see the presence of it depends on whether black is object or white is object. The other is background. So one is the object, the other is the background, black or white. Then the other, if black is the object, then white is a hole. So all these white parts are holes, lacunae. So self-similarity dimension is defined in the number of using the number of self-similar pieces in this pattern. 1 over S is the reduction factor, S is the scale factor, B is the self-similarity dimension. The formula is A is equal to 1 over S to the power of D, and take log. D is log A over log 1 over S, or minus log S. So that's the definition of self-similarity. So the Koch snowflake, if you continue, I showed up to here earlier. If you continue, you get this. One of my students, Tan Nguyen, she did this. I don't know how she did this. I lost patience after doing 3. She went and did this either by hand or I don't know what she used. The fractal dimension is 1.262, and that can be computed using these number of self-similar pieces, these triangles, and the scale. Now that is for self-similar patterns that can be constructed using a rule, and you know what it is, and the formula works. But given a pattern, how do you estimate the fractal dimension? There are a few algorithms in the literature that you could use. So this is the contour given. Contour pixels are patterns. What is inside and outside doesn't matter. The box counting method in 2D says, you can do in 1D also, superimpose a grid of some scale, this box, and count all the boxes that have some piece of the pattern, all the highlighted ones. Change the scale, make the box smaller, using some like half, 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 and so on. And again, do the same thing, and keep doing that. Count the number of boxes with some part of the pattern in it. And then plot that. Log of number of this versus log of scale, 1 over scale. 1 over S. And if it is a fractal, there should be a straight line of this. It's approximately straight line. It's 1.26. The theoretical one is 1.262. We got 1.264, which is good. So for the Cox snowflake, not for this mass. Right? Yeah, I'm showing a mass here, but this is for the snowflake, 1.26. There is another type of pattern. There is a category of patterns called space-filling curves. The Peano-Hilbert curve is defined in this manner. There is this grid at some scale, and you should visit one point in each of these subdivisions. And there is a certain rule of visiting them, and that is, you should visit all the elements in your image without backtracking. You should not visit the same place twice. And the curve should be, it's not continuous, it's not differentiable, but there is a certain pattern so that you visit all of the points in the image, but you must visit all points in a certain vicinity or neighborhood before going farther out to other sub-blocks. Then you are moving farther away. So the idea is you visit the nearest points in some sense, in a certain pattern, and then visit all the other parts of the grid or image. These could be pixels in an image. You're scanning. Instead of raster scanning row by row, visiting elements row by row, because you're going like that, you're going far away from the starting point, and then you come back and say, oh, but then you're close to the starting point, the first element. Then you go like that and come back here. You're again close to the starting point, but you went that far. So this method says, don't keep going like that. Instead, visit all the elements within this block, and then go to the next block. Visit all these, and then go to the next, and then go to the next. There's a rule for this. I won't go into those details. One of my students, Joseph Provin, did his master's on using this pattern to scan digitized images and compute prediction models. We thought we would get better prediction because you're visiting neighboring pixels before going farther away. If you go like that and come back, then the correlation between this point and that point is not much. And then you come back again, there is high correlation. So at different scales, you see this pattern, but if you take this pattern, this is the same, turned around. And you come here, this pattern is the same as that. And this is the same, and that is this flipped. And that is this thing turned. So it is this pattern that appears repeatedly at different orientations and scales. And then you get these other more complex patterns. But this is called a space-filling curve. The entire 2D space is filled by this curve in the sense it visits all the points, the center points of all these little squares. That is a pixel, let's say. It could be some graph, it could be something. If it is a digital image, we can call each of these centers as a pixel. So you visit all these pixels in this quadrant and then go to the next quadrant, but you go from here to here, here and there. That's the basic pattern. But if you take this pattern, the same thing appears here, reflected, reflected. And the same pattern keeps on going. In the next stage, all of this will appear in blocks. So this is that a fractal? You can argue both ways. It's a space-filling curve, that's what it's called. It's a fractal in the sense there is nested complexity and there is self-similarity, the same pattern. And nested, the same thing is appearing here with rotation. So we could call that a fractal too. So breast masses and tumors we have seen. Benign masses are round, oval, smooth, macrolobulated, homogeneous, well-defined, well-circumscribed, sharp edges. Malignant tumors due to breast cancer are spiculated, rough, microlobulated, heterogeneous in density. That doesn't matter in terms of contours and shapes. but it matters in frequency content. Ill-defined, ill-circumscribed, and blurry. So those are from BIRADS and from our discussions with the radiologist. Here are some examples. Going from benign round to benign macrolobulated, malignant microlobulated, malignant spiculated. Contours drawn by Dr. Desertels in the grayscale images. Okay. The ruler method to estimate the fractal dimension says, let U be the length of a contour, but the length varies depending upon your measuring scale. The larger the scale, the poorer the accuracy of measurement. In the sense that this concept is, there is some contour and you want to measure its length, and if my ruler is of this size, if I start from here, the next point will be where it intersects. So this is my ruler size, ruler rather. This is the starting point. Then I say, take this and intersect, like calipers, your divider. You say, okay, next point is that. So I'm measuring that. All of this is lost. And from here I say, where do I intersect next? That. And so on. If I use a smaller one, I don't know, this one. So then I'll measure this, and from there this, and this. So I get that length. I get a more accurate length of the contour. So that is the effect of the scale, or the scale of your measurement, in the sense this dimension of the length of this ruler. So if it is, they always say the contour of a British island, I don't know why it has to be British, it could be Manipal Beach or Malpe Beach. Where is the line? How do you measure it? And it's very jagged. And if you measure like that, depending on your step size, you get different results. So how do you model that? U is C times 1 over S to the power of D, where U is the length of the contour, the whole contour that you measure, and C is a scale factor, and S is the scale rather. C is like how many millimeters that is, your ruler. D is a dimension. The fractal dimension is 1 plus D. You're adding this measure to the Euclidean dimension. If you take log, you get this equation, and if you take the slope of that, you will get the fractal dimension. So in the case of a 2D contour, you can do in 1D, you can do in 2D. So this is a malignant tumor boundary drawn by the radiologist, and if I use this ruler size, that is how I measure. If I use a smaller ruler size, you get a different measure, more accurate measure of all these spicules. Here these spicules, this is completely lost. The spicules don't get measured accurately. Then plot that and get the slope of the plot, and that gives you fractal dimension with some correction factor depending upon the Euclidean dimension of where you started. The 1D signature of a contour, we have seen this before. We could convert a 2D contour to a 1D signal, if you want to call it so, a 1D function. Not a function of time, but space or something. By computing for every point on the contour some function. It could be some function, it could be the Euclidean distance of the centroid, it could be whatever you want it to be. And you're reducing from 2D to 1D, that's the idea. A signature is a measurement of some property of the contour at every pixel or point on the contour. So a 2D contour may be converted to a 1D signature using the Euclidean distance to the centroid. This is just the distance to the centroid. So a smooth contour gives you a nearly sinusoidal curve. If it is a circle, you will get a straight line. If it is spiculated, you get a more jagged curve. So obviously, like using that example of measuring the coastline, it's easier to measure this with a larger ruler, but for this you need more scales. You can do this in 1D also, like I showed. Large ruler, small ruler. So if you want, you may convert from 2D to 1D. If not, do it directly in 2D, it doesn't matter. These are various possibilities. So for that one of those contours, FD is 1.15. I mean, is that a fractal is a question. Perhaps some of these are not fractals. So the dimension is low. If it is a straight line, it is 1. It is not a straight line. Is it a fractal? Not really. I can't see much of self-similarity and scaling. There is similarity, yes, there are some waves. Is there scaling? No. So the dimension is low, 1.1. Whereas for the other one, you get more. I'll show some numbers later. So one of the data sets, this work was done by Pan Nguyen for her master's thesis. And in her work, she had various data sets. One from the MAIAS database, 54 contours, which were further divided into circumscribed benign, speculated benign, and circumscribed and speculated malignant. Dr. Desautels said that categorization is not diagnostically or clinically relevant, just say benign malignant. So from the Foothills Hospital in Calgary, we got this set of contours, well, images, and Dr. Desautels drew those contours. And this also, he drew them. MAIAS database doesn't give the contours, it just gives a circle or a square or something. 37 benign, 20 malignant. So the benigns in the first data set, fractal dimension 1.14 plus minus 0.06 standard deviation, malignant 1.4. Second data set, a better separation. Oh, sorry, this second is MAIAS. MAIAS has this mix-up. There are speculated benigns I showed you earlier, some benign ones, and some malignants are circumscribed. So there is a bit of confusion here in shape. So for the MAIAS database, we got a classification accuracy of 83%. For the Foothills, this Dr. Desautels was involved in this, so he knows for sure that these are benign and malignant. But that is based on biopsy, not radiologist analysis. So we got 94% with just fractal dimension, one number, using the ruler method and 1D signatures of the contours. We got comparable results using the other methods. 2D ruler, 2D box, 1D ruler, 1D box, and all that we did. So similar results, some of them not so good. 2D box counting did not work well on the second data set. The MAIAS data set gave a little lower accuracy than our Foothills data set. If you combine both, we got up to 0.89, 0.9. Not bad. Again, using one feature. It doesn't happen like that. Typically, you have a few tens of features. So let's look at the frequency domain interpretation of this, of fractals and fractal dimension. The frequency domain interpretation is based on the fractional Brownian motion that you must have seen in physics, that a particle could be moving at random, some random walk, and the difference between the position of the particle at time t1 and t2 is proportional to t2 minus t1 to the power of 2h. And h is called the Hurst exponent, and that is related to fractal dimension and the Euclidean dimension in this manner. So the variance of this difference in the value of the function at t1 and t2 is proportional to the difference in the time or displacement to the power of 2h. Depending on what you are measuring, these t1, t2 could be time, space, v could be some function, some value measured. Faraz Olomi, he did his MSc and PhD with me on the knee joint sound signal, vibration signal project. We did a fairly big project on the analysis of knee joint vibration. When one swings the knee joint, if there is some arthritic degeneration as you swing the leg, there could be some creaking sound. And that sound has some diagnostic value. There have been some papers in the 1980s on that. We started our work soon after I joined Calgary in 1984. We explored the application of a number of signal processing techniques to categorize these signals. Dr. Frank and Dr. Bell were orthopedic surgeons. They perform arthroscopy. In arthroscopy, a small incision is made and a fiber optic scope is introduced, and the cartilage surfaces and ligaments and so on are analyzed by looking at the video signal you get. They could also insert in arthroscopy in the small, I think there are two cuts made, one to irrigate the joint and the other to put the scope and view. And the orthopedic surgeon can also insert some minor surgical tools and do some minor repair of torn ligaments or menisci and so on. What the orthopedic surgeons had observed is that patients would come complaining of something and they say, my joint is making sound and it's painful and so on. And imaging techniques don't show such detail. MRI can show, X-ray imaging won't show because of the presence of big bones. You cannot see cartilage, which is only 1 or 2 millimeters in thickness. Cartilage is the tissue covering the bone surfaces. Ligaments are hard to see, but maybe in MR imaging you can see. But as I said, MR is expensive, you have to wait. If you just say, my knee is making some sound, you'll wait for months and years. So they felt that, they saw in their clinical practice that a number of patients who were selected for arthroscopy went through arthroscopy and they found there was nothing wrong. So it was a waste. It's a surgical procedure, semi-invasive, but still the patient is under anesthesia and there is some risk. Whenever you make a cut, there is some risk of infection and other problems. So the aim of this project was to see if the knee joint sounds could be analyzed to understand the nature of the issue. Some sounds could be normal, some related to some abnormalities. Which of the patients would possibly benefit from arthroscopy and reduce the number of patients coming and going through arthroscopy, the selection procedure, and then being found to have no problem. That was the original problem. We went through many algorithms, prediction modeling algorithms, adaptive filters, adaptive modeling. One of the techniques we tried was fractal dimension. Is that signal a fractal? So we did 1D signal analysis. Using the fractional Brownian motion analysis, these are simulated signals. With the Hurst exponent h being 0.2, the model FD is using that formula 1.8, 1.5, 1.2. Smoother curve, little rougher, more rough, 1.8. So we thought that perhaps knee joint signals related to normal and abnormal knees would have some varying fractal dimension. We found the reverse of what we thought would be the case. Normal joints also have some noise, but that is random, so higher fractal dimension. When there is an abnormality, there is some structure to the sound, and then the fractal dimension goes down. So we have to come up with a different interpretation of that. So how do you do this? How do you estimate the fractal dimension? Based on spectral analysis, you obtain the power spectral density. This is 1D. So there's only one frequency. And that should be proportional to 1 over f to the power of beta, what is called the inverse law or power law. Actually, it's called the power law, with the factor beta being the power of 1 over f. It is also inverse. It is inversely proportional to a power of frequency. So if you forget the factor f, it is an inverse proportionality. The path spectral density should decrease with frequency, which happens in most cases, unless it is random, when it is flat. White noise. When there is structure, the path spectrum decreases with frequency. If there is a linear portion, then you fit a line to that and get the slope of that, 1 over f to the power of beta. And d is 5 minus beta over 2. The factor 5, it depends on the dimension, Euclidean dimension of the signal, 1D or 2D. So these are what we call VAG, vibroorthographic signals. More of that in my 1D signal processing, signal analysis book that you saw the first day. So these are normal and abnormal signals. They're all very random. Well, they look like they're random signals, but there is some structure. They're not like the ECG where you can see clear patterns. So these are some examples of the VAG signals and their path spectra on log scale. Log of frequency, log of magnitude, and we expect a linear portion. Decreasing with frequency, but do you want that band or this band? This band is fairly high frequency, from 100 hertz up to 1000 hertz. Perhaps after 200-300 hertz it's all noise, so we took this band to be the significant band, from about 20 hertz to about, what's the band? It's somewhere there, 20 to 300 or something like that. So the line fit is shown there. Now the spectrum is not a smooth function. It has these variations, especially on a log scale. So you still fit a straight line. The abnormal has that slope. Normal 1.8, abnormal 1.3 fractal dimension. We got area under the ROC curve up to 0.75 with a data set of 8 and 9 VAG signals. Just again, one feature. So 0.75 area under the ROC curve is good for one feature. You add more features, you can get better. I'll show the 2D application of that later on. In the case of 2D images, there is a method known as the blanket method. I think I described this under chapter 7. So if you have a flat surface of an image with the same values, you want to cover it with a sheet of cloth or a blanket, you need a certain area of that blanket to cover it. But if this has other things, it is not a uniform surface, you are required to cover everything, you need more of that blanket to cover all of these exposed areas. Everything, every surface has to be covered. So if you have something like this, you go here and come and cover everything. So you require more of the blanket area. So these are pixel values. So the top of the pixel, there is a certain area, depending upon your sampling resolution or pixel size. You have to cover that, cover this, but also these exposed areas in between. If you imagine these to be blocks, like a building towers in the city center. So take these parameters and compute the area as the area of each of those exposed top surface, and then all the differences between the pixel values multiplied with epsilon, and epsilon is your scale factor, and 2 minus the derivative of that and the log scale factor will give you the fractal dimension. Extend that, or rather go back and extend the spectral method that I described earlier with 1D VAG signals to images. You convert the Fourier spectrum, as I've shown earlier, from Cartesian to polar coordinates. And then from polar, you take the marginals versus angle and radial frequency. I showed how to fit a straight line to the radial frequency path spectral density, which is a 1D function for a 2D image. The angle distribution is different, and we quantified using other parameters for architectural distortion. Here, the fractal dimension of the image is related to the slope of the 1D radial frequency pass spectral density. So compute the 2D Fourier transform FUV, compute the 2D pass spectral density SUV magnitude square, transform SUV to polar coordinates SF theta, SR theta, whatever you want to call it. Integrate over theta to get SF, similarly get S theta by integrating on F. Fit a straight line to a selected range of frequencies of the 1D PSD on a log-log scale, 1D PSD on radial frequency. Determine the slope of the best fitting straight line, and 8 minus beta now. 8 because the Euclidean dimension of the image is 2. So using that, one of the equations I showed earlier, then we get 8 here. So here's a region of interest with architectural distortion, Cartesian coordinate, Fourier pass spectrum, polar coordinates, angle, radial frequency. Now this is a fairly smooth one because you are integrating. In the 1D case, you just take that frequency spectrum. That's why it was so noisy. Here, to get this radial frequency, you are integrating on theta. So many values are added. So this is a nice smooth spectrum, easy to fit a line. But we need to specify a range. You don't want to fit a line to the whole thing. There could be some very low frequency information that we are not interested in. There could be some very high frequency part of the spectrum where you have noise. So find a middle range, log-log scale, fit a line, get the slope, get the fractal dimension, beta is the slope. So these are synthetic images. One of our colleagues in the Faculty of Medicine had developed a program to synthesize fractal images using the fractional Brownian motion model. And these are 3 synthetic images. This looks like a mammogram. This also could be a mammogram, maybe even that, part of a mammogram. Model fractal dimension based on the parameter used to synthesize 2.2, 2.4, 2.6, rougher as the fractal dimension increases, rougher texture. Blanket method gave 2.5, 2.57, 2.7, increasing, but the increase is not that much. The pass spectral density method did not give much of a difference. 2.66, 2.67, 2.68. That's not a significant difference. If you take the p-values over a number of such images, perhaps this will be insignificant. This could turn out to be significant from this to this and this to that, or rather from here to there and here to there, maybe not here. But that's not what we wanted to do. One could do such analysis to see if these differences are statistically significant. So we put together a number of shape factors. Tan, for her master's thesis, did this work. Compactness, convex deficiency, I have defined all of these earlier. Points of inflection, get the polygonal model and get the fractional concavity. We saw all of this, right? If you remember. And speculation index we saw. So no need to go through them. Fourier descriptors we have seen, and normalized Fourier descriptors to compute this FF we have seen. So now we have our data set of contours and some examples of this feature vector of fractal dimension using, it is somewhere else. I can't remember which method was used. And compactness, speculation index, the Fourier factor, fractional concavity. Fractional concavity works well. We expect this to increase, A, B, C, D. And all of them are increasing as expected. Okay. The grayscale image, the contour drawn by the radiologist, and a feature vector now. So that's a feature vector. So the data set was rank ordered using fractal dimension. In the publication, we have the details using different methods to estimate the fractal dimension. I have lost that here. So benign, B is benign, M is malignant. Most of the benigns are up there, some malignant. These are misclassified if I put this threshold. As I vary the threshold, I get the ROC curve. Benigns mostly up to 1.3 or so, and then mostly malignant up to 1.7. Another data set. This is the MIAS data set. This is our data set from the Foothills Hospital in Calgary. This is from the MIAS data set. That is the very first one, speculated benign, but it still is only 1.04. So these are going there, and let's say the threshold is 1.28. We have several misclassification examples here, going to 1.5. So in Tan's work, she did various pattern classification experiments using the Fourier factor, area under the ROC curve, 0.77. Compactness gave very good result, fractal dimension comparable, and through feature selection, various combinations were selected. The fractal dimension with fractional concavity gave the best result of 0.93. For the combined data set of 111 contours, a ruler method on 1D signatures for fractal dimension. So there are significant differences in the fractal dimension of contours of malignant tumors and benign masses. The grayscale variation did not give us very good result, but that could be due to the nature of the images we have. Maybe with digital imaging you get better grayscale sensitivity and better representation without much noise, then you may be able to find fractal dimension computed using the frequency domain method also useful. It depends on the type of images you have. In any case, shape analysis using fractal dimension gave us very good results. And when combined with other shape factors, we got even better results. So fractal dimension can serve as a useful feature, one of the features in a set of features, and could also assist in the analysis of biomedical signals such as lag and EMG. There are several papers showing the usefulness of fractal dimension in the analysis of EMG, electromyogram, muscle electrical signals related to contraction and fatigue, development of fatigue. If you hold the contraction too long or do some exercise repeatedly, then the muscles develop fatigue and the signal characteristics change. So how do you characterize that? And how do you characterize different levels of contraction of the same muscle using the EMG? Fractal dimension has been useful. We did, let me say, Dr. Desertel again, Tan did her master's on this topic, Liang did his MSc PhD, Naga did his PhD, Neema came from Egypt and she did part of a PhD, and Hilary did a PhD with me, Shantanu did his PhD, Faraz did his PhD, Lucas came from Brazil and did his work on that vertebral compression fracture. So all of them used some parts of this and gave me some illustrations. Now we did a number of other experiments using full field digital mammograms also from my collaborators in Italy. They gave us a data set of contours of masses drawn by radiologists on digital mammograms, full field digital mammograms, the FFDM. So we had 3 data sets, 2 that we had, and which is which, it's in the paper. I can't remember which is which here. There are 3 data sets. So these shape factors gave good results. 9, these are area under the ROC curve, individual shape factors. But in one of the data sets, the results were not so good. This must be the MIAS data set. This must be the Calgary one. This must be the full field digital. I can't remember. And then we did various cross validation across the databases. You train with this and test with that and put them together or not, and then use different classifiers, linear, discriminant, quadratic discriminant radial basis. I think Dr. Narasimhan will talk about some of these classifiers later. And different data sets, train with this and test with that, all of that. So lots of these results, but sometimes going up to 0.99 with just two factors, two features. Sometimes more features were selected, but the results are poorer. So it depends on the classifier or selection process, which features are selected. So you get different results. 12:30, well, that's good. Any questions about fractals and fractal analysis of signals or images? I'll put up PDF files of all of these new. This is not new, but one will be new, the others are there, but I haven't transferred them yet. At the end, maybe in a couple of days, please look into that Google Drive and download all of the files. Any questions before lunch?
You saw one of the example of the knee signaling. So I want to know that how do you classify the other ends to be noise?
Other?
The data parts to be as noise.
No. From analysis of the signals and knowing the bandwidth of data acquisition, the filters used before sampling, we estimate a certain range to be bearing useful information and certain very low frequency information to be not of relevance in classification, and very high frequencies within that band to be noise. It's just estimated by analyzing the signals and their spectra by visual analysis. The classification of the pathology was done by the orthopedic surgeon. All of them underwent arthroscopy. So the classification of normal or abnormal, we didn't go into subcategories as to whether it is cartilage or ligament or arthritis or something else. We just did screening, normal, abnormal. When I showed that spectrum, what I wanted to emphasize was you have to select a range over which you will fit the linear model. There will be noise, especially in the 1D case. In the 2D case, it was a smooth spectrum, but even then, there is some variation in the low frequency range, and that's not a straight line there. And after that, it goes down, and there is no straight line there, but there is some band where there is this straight line proportionality, where there is a clear straight line over which we can compute a slope to fit the spectrum. If you fit it for the entire range, it will not work well. So we need to define some bandwidth over which we will fit the spectrum with a straight line, and then compute the fractal dimension from there. That is by inspection of the signals. There's no rule for that as such. But from data acquisition, we know the bandwidth over which we have acquired the signal, and by analyzing the signals in our data set, we are able to make some judgment as to where the useful frequency components stop. Then we say the rest is noise in the sense not desirable for this process of fitting a straight line.
So there were two signals actually. We compared the normal one and abnormal one.
Which one?
There were two images comparing with normal one and abnormal one. So for that normal view also we had to take the signals this way to quantize the other abnormal one.
For the normals also, what?
We had two pictures there.
Yeah.
The signal of the normal knee and the abnormal knee. So to quantify this abnormal one, did we take signals of the normal knee as well?
Yes, we took signals from all the patients who were scheduled to go on arthroscopy during the period of our study. We also took signals from patients who had gone there for examination, and they were found to be, by clinical observation, to be normal. Not all of them went through arthroscopy. That categorization was done by the orthopedic surgeon. And we had volunteers also from our department and neighboring departments to go, but they would be evaluated using some questionnaire to determine if they are normal or not, meet the criteria for clinical definition of normality, and then the signals were acquired in the lab. Yes, so we did acquire normal signals also. Is that what you asked?
Yeah.
Yeah.
Thanks.
So it's kind of a detour from what we are talking about, but this is as regards getting this MOA, with the clinicians. Because I faced a similar problem when I started working on my stuff in CXR, like a chest X-ray. So I approached a couple of hospitals over here, and I just wanted them, kind of to get affiliated with them so that they can provide me the clinical insights. Because the VNDR CXR I got has only bounding blocks, there's no specific ground truth, as regards to what I'm looking at. So most of what they said is they normally bring the problem statement to us, and not us going, we design something and then we want them to, give their insights. So I wanted to see, know how is it like over there? Because I remember I visited ISC, Prof. Pandya is there, like a young researcher. So there I met most of these radiologists. They actually came with the problem statement, and they were there in the university, talking to them and showing them things. So I want to know, how is the research scenario over there? Like, is it like, they will tell you exactly, or you just have to?
Yeah, I think there has to be a lot of give. There has to be a lot of give and take and discussion. It doesn't happen in one day. What I have said in my book and what I tell when we discuss points like that is we need to go around and talk, knock on doors. And just like politicians come to you and knock on your door and ask for your vote, I'm not asking for anything when I go there, but I have to go there. I'm interested, they're also interested, but they need to know what I can offer, and I need to know what it is that they want. So soon after I joined the University of Calgary, I had prepared some seminars on what I had done before that, and then I went and met them. I called around and asked them, I want to do some signal processing, biomedical signal processing. Is there anybody interested? So we went to cardiology, and I had a couple of students, collected some heart sound signals and so on. And they said, well, heart sound signals, we're not interested. I was a bit surprised. I said, well, they said we have ultrasonography now, we don't use heart sound signals. What is this thing hanging around your neck? Everybody has a stethoscope. Nurses have stethoscopes and doctors have. So this is hanging around your neck, and that's your symbol of your profession. And the first thing they do is check your heart sound. How can you say heart sound is not relevant in diagnosis? But anyway, they didn't want that. Then I said, what? And then we discussed various projects in cardiology. Nothing clicked. And then somehow I got introduced to Dr. Cy Frank in orthopedics, and he said, well, we had a joint injury and diseases research group, later on renamed as Joint Injury and Arthritis Research Group, a very multidisciplinary research group with orthopedic surgeons, clinical specialists, and various medical specialists, mechanical engineers, civil engineers, and electrical. So they said, okay, we have a research group, we have weekly seminars or whatever, monthly seminars, come and talk. I went and talked about some signal processing, ECG or whatever I had. Well, they said, oh, that looks interesting. We have these signals, we have knee joint signals. So they didn't want ECG and heart sounds, they wanted knee sounds. I said, a signal is a signal. Tell me the difference between A and B and we can do something. And that's how the knee project developed, and we worked for many years. We had to collect signals. It took months and months. And one of the reasons we have long list of authors is we had two orthopedic surgeons. We had a medical science student. She was handling the patients and recording the signals. I had a postdoc fellow who was doing the signal acquisition and bringing the signal to the computer lab. And I had a grad student. So the list grows. So it is not just me sitting and writing this paper. Impossible. So two orthopedic surgeons, a medical science student, a postdoc fellow, and a graduate student, and myself, 6 authors. So when this goes to the Dean of Engineering, the Dean says, wow, why do you have 6 authors? What is your contribution? I can say without me this wouldn't have happened. That is selfish. And so, but then it is a team effort, right? So there are some, we call them bean counters in administration, even in university administration, and in granting agencies. They say, oh, you are the third author, and there are 6 other authors. What is your contribution? Divide by 6. Okay, whatever. So this is how the projects develop. That discussion takes months. To develop this knee joint project, it took us months. And we wrote a few conference papers along the way that, well, this is what we have explored and studied, and this is what we have recorded. And it grows, the database grows, the complexity of methods. We try the known methods first: linear prediction modeling, spectrum analysis, then adaptive modeling, adaptive filters, fractal analysis, and various statistical measures. How do you break the signal into stationary parts? So it goes on then. Once that relationship is developed, then we can bring in all the advanced signal processing methods that we would like to try. And the interpretation is still in consultation with the orthopedic surgeons in this project. Similarly, I went to radiology and said, well, I'm interested in medical image processing. And the head of the department said, go and talk to Dr. Desertel. Before him, there was a Dr. Morish. So they said, okay, come and tell me what. And I said, X-ray images. And well, chest X-ray images, I don't need anything. Mammograms, we need help, because mammography screening was new at that time. So then, yeah, it switches. But I had worked on mammograms before. I knew about the screening program, and they tell me more. And then slowly it starts. We will enhance contrast, we will detect calcifications, and you saw that whole story. So that takes 30 years of work. So these things won't happen in a matter of a day or two. But that's why tenure is important. I'm a tenured professor, then things can go slowly. The other question that I'm asked often, sorry, I'm taking a little longer. Other question I'm asked often is, did you develop a product? Has your method been useful? How many patients did you save? No, I cannot claim that I have saved even one single person. That's not the idea. We are professors and we are researchers, and we add to the knowledge base. And there are some who recognize that. Not many people recognize what is this knowledge base. All the papers that you write, all of you write papers and publish in conference proceedings and journals, that is the knowledge base. And you write about this, and the next person writes something more, better about that, and better, and the knowledge base grows. So based on all of that, the next generation will be smarter and better. So in Telugu there is this Guru Minchina Shishyudu. They say, so how can the student be better than the teacher? But that is possible. It has to be so. Otherwise there will be decay, right? So the next generation has to be smarter and better. So there is nothing wrong. You can't claim that. I won't go and tell my professor that I'm better than you. But based on what I learned from him, I have other experience. And based on all of this, you should have something more and develop something better. And when you give that to your student, that student should do even better. And that's how the knowledge base grows. And to take this to clinical practice is a totally different thing. I'm not a business person to develop a product and sell it. Even patenting, many of our professors, and I also took the opinion that we will publish, put it in the public literature. This was funded by government sources of public money, or cancer societies that have raised fund by public donations. You give $5, $10, and they give us some grants. So that is public money. So I can't hold that and say I'll get a patent and I'll make money. The university wants a cut of that too, of course. But the university can help in getting the patent. Getting a patent takes 3, 4, 5 years. Turning that into a product, that is totally different. There's no research involved there. And I want to do research. And the thing is published. You are interested in develop a product, go and do it. Not mine, There are hundreds of such methods. You select the best, compare them, and develop your product based on what you find to be the best available method. Will you make money? I don't know. But to take that to the level of a commercial CAD system, it takes years and millions of dollars of investment. And that's not my interest. Right? There are some who may be interested in doing that. Fine, go ahead and do it. But that's a different path. That cannot be done without this knowledge base. Somebody has to create this knowledge base. Anything else? Lunch. Okay, 12:45, we come back at?
1:30 possible?
Oh, no, that's only 45 minutes.
Okay, 1:45. 1 hour session. So 1:45 to 2:45. So 2:45 to 3:15 is the break. 3:15 we start with the procession last.
Okay. Okay, so we'll start where we have left in the last class. But before that, we just define the two-class classifier. So we define the two-class classifier as this. The classifier takes 1 if the discriminant function value is greater than 0, and it takes -1 otherwise. So this is the definition that you see for the two-class classifier. Suppose if f of x is linear, then the classifier is a linear classifier. It is of this. So h of x is equivalent to 1 if this is greater than 0 and this takes -1 otherwise. So this is the definition for the linear classifier. So we have taken example in the last class, and we have seen how we can train the classifier. There are many methods to classify the linear classifier. So one of the method is the least square method. One of the method is the least square method. So we have seen this method, and the second method, popular method, it is the earliest method. The method is called the perceptron algorithm. So people use a perceptron method, perceptron algorithm approach to train the classifier. Perceptron algorithm. So we can use this algorithm to train the linear classifier. There is another method, which is popular method. Still people are using this, which is the linear discriminant analysis. So these are the popular methods that are available in the literature, which are being used for training the linear classifier. We have seen the least square method in the last class. What is that we do in the least square method? We get the error function, we try to minimize, the error function with respect to the parameters. But how do you implement that on the computer? Do you have any idea about this? Do you have any idea about what you do on computer? How you implement? So we already seen in the last class is if I use this method, I have to solve the system of equations. If you say I have to solve the system of equations, I have to invert the matrix, right? So people don't prefer to invert the matrices on computer. Usually, if you have a more number of samples, you have to invert a big matrix. That people don't want to do. It's not advisable to invert the matrix and do it. So instead, what they do is that they apply algorithm. What is that algorithm? They apply the steepest descent algorithm. They apply steepest descent algorithm. It's an iterative algorithm. You know already. What is that? Yesterday, Shamla sir was showing, what is the updation step in the steepest descent algorithm. You already seen. So this is the algorithm that being used to get the least square solution. The least square method gives you a least square solution. So if the least square method, when I use the least square method to train this, it happened to be you have to solve the linear set of equations. And we don't want to solve the linear set of equations, so we take up the steepest descent algorithm to get the least square solution. What is that least square solution? The least square solution is this. This is the least square solution. You might have seen in SAS PPT this equation. This is called the least square solution, where A is the data matrix. A is formed by the data samples that we have, and Y is the labels. So how we arrive at this formula? We need to have one more class to understand this. Okay, how you arrive at this? Okay, but time being, you just take it this. Okay. Okay, now the next algorithm that you see here is the perceptron algorithm. The perceptron algorithm can be used to train the linear classifier. But the condition is, what is that condition? The condition is that we already see the data, right? Simple data from the last class. What is the data that we have? This is the data we have, right? We have the one-dimensional data. We have 3 samples, right? This, the sample value, the feature value belongs to class 1, and this feature belongs to, again, class 1. The feature value is 2, and the third feature value is 3, and it belongs to class 2. Now look at the feature space. This is called the feature space. This is called the feature space. So one-dimensional feature space. Now look at the pattern of the features. You can see that the features are linearly separable. The features are linearly separable. What do you mean by linearly separable in one-dimensional? You can get a point. Which can separate the 2 classes. So you can have a point here. You can have a point which can separate the 2 classes. If this is there in the feature space, then you can apply the perceptron algorithm. The perceptron algorithm you can apply this to train this if the feature space is like this. If the feature space If the features are not linearly separable, then you can't apply the perceptron algorithm. Perceptron algorithm is basically an iterative algorithm. It's an iterative algorithm. It will converge only if the data, the feature samples are linearly separable. So for example, if you take the two-dimensional case, right? So let's say you have some data is something like this. Right? You have data something like this. If you have something like this, you cannot get a hyperplane, you cannot get a line which can separate these two classes. There are two classes here. This one, these samples that you see here belong to a class 1, and these samples belongs to class 2. You cannot separate the two classes here by a line. You cannot separate. You cannot see if you have something like this. If you have something like this in the feature space, let's say this is a two-dimensional feature space. If you have a feature space something like this, then you can apply the perceptron algorithm. I am not going to discuss about the perceptron algorithm. It's a simple algorithm. I am not going to talk about the algorithm. So just I am telling you how, when it works. This works only if the feature samples are, the classes, two classes are linearly separable. In the one-dimensional case, you can get a line which can, right? If you can get a line which can separate this, then you can apply the perceptron algorithm. But the perceptron and iterative algorithm, when you say iterative algorithm, we need to talk about the convergence of the algorithm. The algorithm converges if the two classes are linearly separable. Okay, the third one is the linear discriminant analysis. What is that they do in this is, they take the feature values, they take the features, the feature values, the feature vectors, and they look for a W which characterizes a plane. They look for a W. They look for a W where your projected data is linearly separable. So in the linear discriminant analysis, they find a W vector, right? With which you can do the projection of the data onto that, and you look for the separability of the data. So you look for a W where you then you project these features onto this W, so that your data must be linearly separable in that projection space. So you do the projection, you look for a space, the projection space, right, where your data must be linearly separable. You look for a W on which you project the data, on which you should see the linear separability. Okay, right? These are the ideas of these three algorithms. I'll not be getting into this. Right now, what I do is that I'll define the classifier differently. Let's say the h of x is equivalent to the sine of W transpose x plus. What I do is that I just rewrite this in another form. I can write like this. I can write like this, right? If this is positive, what is that classifier takes? If this is positive, what is that it takes? If this is positive, what is that? The classifier 1, right? Sign of this, right? So it will give you right 1 well. And if it is negative, the minus 1 it gives. So I redefined this as this. Now this is, but how do you realize this? How do you realize this? How do you realize this? So what we do here, basically, we do, the perceptron, there's a device which can realize this. The device is called the perceptron device. Yesterday Shamla was telling, right, perceptron model, right? So we are coming to that. Okay. So the perceptron model. So here, what is that? We are. See, this you can think of. What is that you can say here is that we can think of this as, finding the weighted sum and thresholding. So what we are doing is that we are, what is that we do here is that find the weighted sum and do the thresholding. That's what we are doing here, right? So basically what we do is that we weight the inputs right, and then we weight this, we find the weights, we multiply these inputs with the weights W1, W2, W3, Wn, and then we give it to the summer right here, and then we do the thresholding. So this is how you can realize the linear classifier. The perceptron device actually realizes the linear classifier, and we need to add we have forgotten one thing here, right? What is that? What is that we have forgotten here? Bias term. What happens if you don't give the bias term? What happens if you don't I am not going to give, right? If you don't give the bias term, what will happen? What would happen? So we have already solved this problem. Okay. From the last class, what do you say? What happens if you don't give the bias term? So what will happen is that every time if I don't give the bias term, it will say that the threshold is, what is the threshold that we have found last class? The threshold is somewhere here, right? So if x less than 7/3, then the classifier says it's 1. If it is greater, the classifier says -1. Now if you don't give the bias, what is the threshold that it gives? Always 0. See, it always gives you 0. See, what would happen? The threshold means, you see that, what is that equation? Last class we had linear equation. We had this, right? No bias term here. 0. Right? See, if A we found A is -1. If there is no A naught, what would happen is that it always says that the classifier says that what it says, if the h of x is equivalent to if x greater than 0. This is what happens. Always see, for example, in the two-dimensional case, you see that if you don't have the bias term, what would happen? If you don't have the bias term, suppose you have the feature space is something like this. For the two-dimensional case, what is the linear discriminant function? A1 x1 plus A2 x2 A1 x1 plus A0 is equal to 0. Yeah. I mean, this is the threshold that we use, right? This is the. So if this is not there, what would happen? If this is not there, is a linear equation which always passes through origin. You can't, get a line which can separate these two classes. So you can, if you say like, right, if it is in n-dimensional, right? You suppose you are handling n-dimensional data. So you cannot get a hyperplane. You can get a hyperplane which always passes through origin. That's the difference, right? So we should have always the bias term. This overall structure is called what is that? This is this. So we have used multipliers and summers, right, and the threshold, right? We have used many things here. So what is this called? This is called the neuron and the perceptron. This is called the perceptron. Perceptron. Now what is the problem with this? What is the problem with this? How do you train the perceptron? How do you train the linear classifier? Of course, you can use the perceptron algorithm to train your. But what is the condition if you want to use the perceptron algorithm? The classes must be linearly separable. But it's not always the case. Okay. So we need to use some other algorithm. Okay. Or maybe you need to use the least square method. Right? So this is the classifier that we need to train using least squares. So what is the problem with this classifier? How do you train? We need to. What is the meaning of the training? Updating, right? Getting this, right? So to train this, training means minimizing the error function. So what is the error function that we have used in the least square? We have the error function is equivalent to sum of the error squares. Okay, sum of the error squares that we have, right? So if I take that, the problem here is that we cannot do the derivation. We cannot compute the derivative. There's a problem with the derivative, and also the problem here. One more problem is, this may not be equivalent to this. This may not give you. If I do this approach, this may not be equivalent to the efficient classifier, which is a Bayesian classifier. So for that, what they do is that they change the threshold strategy. What is that they do is that they apply. What they do is that the classifier takes 1 if the sigmoid of W transpose X A naught is greater than 0, and it takes 0 otherwise. They change the threshold strategy. Instead of this, they apply a function called a sigmoid function. Sorry, right? So what is that here? I mean threshold. If I apply the sigmoid function to this, what is the threshold here? What is the threshold? We have already checked. We already seen, right? What is the threshold? Right? What is that? Is greater than. If it is greater than 0.5. If it is greater than 0.5, then it takes 1, otherwise 0. Now you can easily train this. You can easily train this classifier. You can get, you can easily train this classifier using least squares. you can get the error function. Okay, you can easily take the derivative of that, gradient of that. You can do that. Now, if this would give you the values in the range of 0 to 1. Right? So you can define this classifier here in a different way. What is that? How you can define is h of x is equivalent to 1, right? If the probability is high. Probability is high, which is greater than half. Otherwise, it is equivalent to 0. This implies is greater than 0. If this is greater than 0, if this is greater than 0, the sigmoid of this will always be greater than 0.5. We already seen, right? What is the sigmoid function? Sigmoid function is this. At 0, this is with respect to this. We already seen, right? So at 0, what is that you get? You get 0.5. At infinity, minus infinity, this is 0, and infinity, this is a 1. So this is something like this, right? This is sigmoid function. There is another way to train this classifier. What is that we do, right? There is another approach. Maybe you are familiar with this. So this classifier gives you two types of errors. Okay, two types of errors. The feature vector may belong to the class 1, but in the classifier may say, right? The classifier says that the x belongs to may say, right? It may belong to class 2. It actually may be class 1, but the classifier may says it may belong to class 2. That is a one error. Okay. And the other error is, what is the other error? Xi may belong to class 2, but the classifier may say that it may belong to class 1. There are two types of errors, and the loss you incur but the two errors would be different. So this is one kind of error. Now other error is this. Error 1, right? Okay, this may be class 2, and h of x may says that xi belongs to class 1. There are two types of errors. Error 2. Okay, so two types of errors, two types of losses you get. So for the class 1, what is, I'll define the loss. What I do is that so basically we need to train this, right? So what is training means we have to minimize the error, right? Given by the initially given by the classifier. Okay. So we can have a loss for separately. We can have the loss for the class 1 and class 0, class 2. Let's say class 2. What is the loss function that we can define for the class 1 is, let's say the probability that you get here is the GW comma X. Okay, this is the probability. Okay, let's say this is equivalent to this. This would give you probabilities. Let's define this as a probability. Now I'll define the loss for the class 1. The loss for the class 1 is this. I define for the y is equivalent to 1 for the class 1. I define the loss function something like this with respect to the class 1. I define something like this. Why this is a, this must be like this. Why we are bringing log here? Because probabilities are there, right? So we define the loss something like this. If I plot this with respect to the probability, for the higher probability for the class 1, we know that the sample belongs to class 1, right? And if the classifier says, if the probability, if the probability that you get here is high, we should incur the less loss, right? So if I use this, what would happen is that for the higher value of probability, what this becomes, how this graph would be, this is something like this. This is something like this. If let's say the sample belongs to class 1 and the probability is high, the classifier is giving higher probability, then we should incur no loss. So the loss is almost 0. Your sample, we know that your sample belongs to class 1 and your classifier is giving you higher probability, then we should incur less loss. So this goes to 0. Yeah, in fact, right, so it will go like, it is something like this, right? This is the loss function for the class. This is the loss function for the class 1. What do you expect the loss for the class 2? Y equal to 0, right? So your sample belongs to class 2. Sample belongs to class 2. What is the function? What is the loss function what is the loss function? The loss function for the class 1 is this. And what is the loss function for the class 2? We should get, the low loss. We should get low loss for the lower probability. So we know that X belongs to class 2. So the classifier should give a lower probability. If the classifier gives you lower probability, then you should incur, right, no loss, right? So your graph may be something like this. The graph may be something like this. It will go like, see, for the higher probability, the classifier should not say that for this sample, if xi belongs to class 2, the classifier should not say that, classifier should not give you lower probability, right? If the classifier gives you lower probability, then what is the loss here? Very high loss. Very high loss. See that it will go up. And this is the loss function for the class 1, this is the loss function for the class 2. Why we are saying this? Why this is like this? Why this is 0 for the higher probability? We know that the sample belongs to class 1. And if the classifier says, if the classifier gives you higher probability, we should incur low loss. If the probability is low for this sample, then we should get high loss, because we know that this sample belongs to class 1. Let's say this sample belongs to class 2. We know that the xi belongs to class 2, right? If the classifier says that it's a high probability, if it is high probability, what it says, what it takes, the classifier gives you class 1. But we want this to be classified correctly. If this classifies correctly, then we don't need to incur any loss. Okay. Now, with respect to these classes, if you combine the two losses, with respect to these, right? With respect to these two classes, you just combine the loss. So if I combine with respect to the two losses with respect to the right, the two classes, let's say this. Right, so what is the loss function that we have to take here? We have not given the loss function here. What is the loss function? See, minus log of 1 minus, this is the loss function. See, for the class 1, this is the loss function. For the class 2, this is the loss function. And you combine the two losses with respect to the the class 1 and class 2. What is that you get is, any idea what is this called? You already know this. Sorry, this probability, this loss function is this. Say, right? Okay. Okay. So what is this called? What is this called? What is this called? Any idea? This is cross entropy. This is called the cross entropy. See, the cross entropy compares the two distributions. So for the given samples, you get two probabilities here. You get a probability for the given sample, you get the probabilities. These probabilities given by the classifier, and we have the true cross probability distribution. What is that? 1, 0. So basically what we are doing here is, right, we are comparing the two distributions here. We are comparing the two distributions here. If the two distributions are same, then what is that you get here? The two distributions are same. What is this? The cross entropy is what? The two distributions are, right? Two distributions are same. Let's say classifier also, this is also 1 and this is right, if it is 1 and this is obviously 0, right? What would happen? If this distribution is the same, then 0, right? So the cross entropy is 0. The information that you get is 0. Right? Entropy is nothing but the information, right? So information that you get from the. Okay, so now we need to minimize this. Minimize this. So you can use steepest descent algorithm to minimize this, okay, with respect to W. Okay. So what is that we have done? We have just slightly changed the perceptron. We have used a different threshold mechanism here, right? Why we have changed the threshold mechanism here? To do the in some sense, if you getting into pattern recognition, you will come to know that in some conditions, this function would give you the posterior probabilities. This function estimate the posterior probabilities, and also it is easy to take the derivative of that. That's why we slightly change the the threshold mechanism over there, right? So this is the error function. You need to minimize this with respect to W, right? Then you get you can define the classifier there. But however, this can only classify this is called the linear classifier. However, this is called the linear classifier. This does the linear classification. Does the linear classification. It can only solve the problem. What are the problems it can solve is, suppose, let's say you have the two-dimensional data, something like this. Suppose you have the one feature here. Let's say this belongs to class 1, and here you have another feature, right, which belongs to the class 1, and we have another feature here. Let's say this, right, 0, 1, which belongs to, let's say, the class 2. This is a class 1, and this is a class 1 again. This is a class 2, and there is one more feature here, which is 1, 0, which right, say this belongs to class. So you have two features here, x1 and x2, and we have the corresponding classes for those feature values. Right? x1 is 0, x2 is 0. It's a one feature vector which belongs to class 1, and this is another feature 1, 1, which belongs to class 1. And this is another feature which belongs to class 1, class 2, and this is another feature which belongs to class 3. And you look at the feature space here. You cannot get a line which can separate the two classes. This problem is called, you might maybe knowing that this is called the XR problem. If you look at the truth table of the the XR gate, right? So let's say this is right, 0 0 1 0 1 0 1 0 0. This is XR or XNOR? XNOR or XR, whatever, right? So XNOR problem or XR. This is called the XR problem. You cannot solve this problem using this classifier. Though you use this threshold mechanism, still it can only solve the linear problems. What kind of problems it can solve? It can only solve the problems which are the R problem or AND problem. So this one that you see here, linear classifier, only can solve R and X, the AND problem. What do you mean by that? Right? let's say your feature vectors, right, the feature values, the feature vectors belongs to, let's say this belongs to 0, the class 2, and this belongs to class 2, and this belongs to class 2, and this belongs to class 1. Let's say you have the features like this, and the corresponding classes are like this, and this is called the AND problem. AND problem can be solved by the linear classification. You cannot solve the problem that I have posed here. The XR problem you cannot solve. And you can solve the R problem as well, right? See, what is that? See, if I plot, if I depict this on the two-dimensional space, right? 0, 0 belongs to what? Class 2, and 1, 0 belongs to class 2, and 0, 1 belongs to class 2, and 1, 1 belongs to class 1. Now, can you get a line which can separate these two classes? Fine, right? So you can get a line which can separate this. But in this case, you cannot get a line which can separate them. The perceptron, or the modified, this one only solves the linear problems. You try out, you try like with the perceptron, or this one, this classifier. You can only solve this. You take, right, what are the W's, right? So how you define the classifier? Getting a classifier means getting the weights. You take, whatever the combination of weights. You cannot solve the linear problem. You cannot solve this problem. This problem is called the XR problem. You can only solve the linear problem. So what they have done is, to solve these problems, what they have done is, so what is that? How do you solve that problem? The problem can be solved by a neural network. With at least one hidden layer. If there is no hidden layer, it is something like, the classifier is a linear classifier. You cannot solve the. What do you mean by that is, so for example, this problem can be solved by neural network, a specific neural network of this. Let's say input, these are the neurons, just passes the input. Here you have a this is called the output layer, and this is called the input layer, and this is called the hidden layer. Input layer has 2 nodes, hidden layer has 2 nodes, and the output layer has one node. Without this, what people found is, without this hidden layer, you cannot solve the. So what is this? What are these nodes actually? Each node is of the linear classifier. Each node is basically the perceptron with the sigmoid function. Each node that you see here, perceptron with the sigmoid function. Each node. So what we do is that generally to get a neural network, what we do is that we take the perceptron with the sigmoid models, and then we interconnect them to form, to get the neural network. So what is the neural network actually? The neural network is a composition of you would say that the interconnection of the perceptron with the sigmoid function. This can only solve the linear problem. One can show that this cannot solve the nonlinear problem. This cannot solve the problem that you see here, XR problem. But this can, this network that you see here can solve the XR problem. If you interconnect these models, right, like this, then you would be able to solve this. And these are the networks that can solve these are the networks that do the nonlinear, that is the nonlinear classification. The nonlinear classification. In the literature, right, people generally use a particular type of neural network. What is the neural network that we use always? We always use the feed-forward network. Feed-forward network, neural network. What do you mean by feed-forward network? What do you mean by fully connected feed-forward network? We usually use, right, when somebody says neural network, right, so immediately we think of the feed forward, or the fully connected feed forward network. Okay, so what do you mean by that? So let's say input layer has many nodes, something like this, and let's say you have a hidden layer, one hidden layer. There are many nodes, maybe you can say like more. And you have one output layer here, one node in the output layer. So this is the input layer. You have so many perceptrons here with the sigmoid function, and this is the hidden layer. You have so many perceptrons with the sigmoid function, and we have a output layer. Okay, what do you mean by fully connected feed-forward network? What do you mean by fully forward? Right? Every node is connected to every node. Okay. So this node, the output of this is connected to every node. This node output is connected to every node of the hidden layer. And all the outputs of this hidden layer connected to this. Right, so you can say like, right, so yeah. So this node output also connected to all the nodes here. Okay. And there is a weight connection between these nodes. There is a weight connection between these nodes. The weight connection between these nodes. Now you tell me, what is the difference between the neural network and the convolutional neural network? There is something called convolutional neural network. What is the difference between the neural network, the feed-forward network, fully connected layer, right, what is the difference between the fully connected layer and the convolutional layer, convolutional neural network? What is the difference? What are the main differences? Why people are crazy about CNNs? Why people shifted from this to that? Why can't they use this neural network over the CNNs? Why people go for CNNs? Huh?
When you go to image data set, when you have more dimensions, so you start with
in convolutional neural networks also you find the perceptron of the sigmoid function, remember. Okay, so you have nodes. Okay, you have so many perceptrons, basic models. Yeah, you're right. See, I mean, we use we put it the convolutional neural network in a different way, right? To to accommodate for the images. Okay. But what is the main difference between here? What is the main? Suppose let's say this is a 1D CNN. See, what is the difference between 1D CNN and the fully connected layer? Don't go to the image and all. Okay. What is the difference? What is the main difference? The NNs and CNNs. Convolutional neural network and NNs. Why the people have dumped this? Why people are not using this? What is the main difference? You see, in the fully connected layer, every node output, right? This output is connected to every node of the next layer. That won't happen in CNNs. That won't happen. So this output only connected to the few of the nodes in the next layer. So there would be a sparse in connectivity. So the first advantage is, what is the first advantage? Sparse connectivity. Sparse connectivity. That's the main advantage. It's the main advantage of the first advantage. What is the second advantage? The second advantage is that, so it will not be, so this output will not go to all the nodes. This output only go to a fewer nodes here. Okay, you can think of this as a 1D CNN. Okay, don't complicate yourself right. So only this output will only go to the 3 nodes here. Okay. Now, what is the second advantage of the CNNs? What is the second advantage? Parameter sharing. Right, is this correct? Parameter sharing. What do you mean by parameter sharing here? In the fully connected layer, every node is connected to every node of this. There is a weight connection. There is a different weight connection that you see. Different weight connection. W1, W2, W3, W4, W. There's a different weight connections that you see in the fully connected layer. The parameters, the weight connections won't be shared in that. The parameters won't be shared. But in CNNs, what will happen is that, right? So the same weights will be shared throughout this. The same weights would be shared. Yes.
This is due to the formulation, our formulation of convolution in terms of matrix multiplication.
Yes, correct, sir.
When we had the same values being
Yeah,
shifted, we got that Laplacian matrix as we saw.
Yeah, you can think of the here, as a 1D convolution.
Yes.
Yeah.
Is that because of that formulation of convolution, or is there some other reason for this sparse connectivity? If you take the,
No, the sparse.
neural network for pattern classification, we need the full connectivity.
Yes, classification. See,
Of images with a small matrix of the filter function where the sparse property comes up. Is that correct? Because of the formulation of the image as a column vector,
yes.
because of the formulation of the convolution kernel function, as we saw yesterday in Dr. Sharda's presentation,
The same kernel,
minus 1 or plus minus
yeah, the same kernel will be, will be applied, throughout, the image.
that is because
So,
of the formulation.
Formulation, yes, you're
Or
true.
some other magic
Yeah.
property. It's because of the
Because of the property. That's one of the property of the CNNs. That way we define, and it will come like that. Okay. So, right, these parameters will be shared here. So you don't see the different weight connections, in the other one. So these the same parameters, right? Suppose if you are, using if you say like this is a 2D network, right? You have a right. So what will happen, right? So what? See. So what is that you do, right? And what is the input to the CNN? The input to the CNN is a image, right? Image that you give. Okay. And what do you do in each and every layer? So you do the convolution operation, right? So you take a kernel, right? The kernel is 3 by 3 size. Okay. At each computation, this kernel is going to cover only the 9 pixels of the image, and those are the inputs to the perceptron. And what are the weight connections here? The weight connections are the filter coefficients, right? So let's say this portion is covered by your kernel, right? W1 to W9, right? Let's say there are 9 pixels, right? 9 pixels are here, right? This is, let's say this is a 3 by 3. See, it covers 9 pixels here. Now what do? You take, right, multiply these weights with the corresponding pixel values and then sum it. So you can think of, right, what you are doing here. Let's say these pixel values are x1 to x9, right? And you multiply these with the W1, W2 to W9, and what do you do here actually? What do we mean by the convolution? You just do the multiplication and take the sum. What is the extra thing that you do? You pass the output through the sigmoid function. That's a nonlinear, to create a nonlinearity in the network. If there is no sigmoid function, Shyamlal sir was mentioned yesterday, right? If there is no sigmoid function, the whole network is a linear network. The whole network does only the linear classification. It won't do the nonlinear classification. So, right, each computation is to do with the one perceptron. We multiply with sum, right, and then, right. So this is called the one convolution operation. Okay, it's a one computation of the convolution operation. Okay, and we pass through the sigmoid function. That's called the nonlinear layer. See, if you look at convolutional neural network, you see there are different layers. One is convolution layer, followed by what you call the nonlinear layer. People generally call it as a nonlinear layer. Then you have the max pooling layer, and followed by convolution layer, again a nonlinear layer. Okay. So implicitly you don't see the the perceptrons with the sigmoid function, but explicitly you don't see that, but implicitly you can see, right? Implicitly you can see that what we are doing in the convolution layer is this. So you know the difference between the neural network and the CNNs, right? So in CNNs, we do the sparse connections. There would be there is a sparse connectivity, and in addition to that, there would be a parameter sharing. These are the two main differences between the neural network and the convolutional neural network.
And also, I suppose in this case, those masks or those weights are predetermined because you know the convolution mask. Whereas in classification, you have to estimate the W, as you said earlier.
Yes. So here also we need to, these are learnable parameters. So you are not going to fix these parameters. So but it turned out to be the parameters, the parameter values in the initial layers. What you would see, the parameters layer, right? If you look at the kernel in the initial layers, you would see maybe something like this. Maybe this does the edge detection. I don't know. Maybe So you find this kind of kernels after you learn the network at the first layers. You find this kind of kernels. So you would see after if you plot the images at the after the first layer. So you take the images, right? The convolution first layer outputs, and then you plot. You would see that how the output would be something like this, right? The output that you get is the edges of image, because after you learn, your kernel turn out to be this, and if you apply this kernel to your image after training, you give the test image, right? So after the at the end of the if I take the output of the first layer would be the edges of the image. Why? Because the kernel is of something like this. It will come out like this. Yeah. So any doubts, sir?
It is known from biological vision and human visual system studies that our eye does bandpass filtering in multiple scales and multiple channels at the first stage. So
similar
what you say connects with human and biological vision systems. But how do you say that this is automatically learned by the system? How does that system match the initial stage
it's
of
very
image analysis in our retina?
that is too complicated, sir. I don't have the answer for that. But see, the neural model that we have is not a static model. The model that we have is a dynamic model. Whatever we see here, it's a static model. This is a static model, and the whole network, does not mimic your brain. It's approximation of what you have in your brain. So people have come up with different models for the perceptrons. So people tried dynamic models. So they were getting something, they were seeing something. I don't know what they're like. I have not done anything. I have not done any experiments on that. So they are coming up. They are seeing something. Okay, what you are saying, like maybe the networks. If you have dynamic model on this, maybe you see something similar to what you see with the naked eye. Probably, I don't know. Maybe with the dynamic model, maybe exactly replicates our neural network, our nervous system.
Thank you, Gian. We have a tea break now. Maybe.
Good afternoon. Today talk, my focus will be on 2D deep learning algorithms for liver cancer detection and grading from histopathology images. The whole work is done at NITK Surathkal, and also we have created a data set for the globally for the researcher as well. And the outlines are as follows: bit introduction, then one of the important thing is teaching machine how to interpret medical data, then digital pathology is the main focus, then neural network study already we had discussion on that, so that not much relevant, and some more application of the deep learning architectures in a healthcare I'll be just highlighting as well, and open source healthcare data for deep learning model which used for in mainly for histopathology applications, and then finally deep learning architectures for classification of liver cancer grades from histopathology images, and then little bit of healthcare research conducted at NITK Surathkal. You'll see the glimpses of my lab, and then future research directions as well in these directions. So this slides already we had discussed my study talk, right, lectures. So these things like AI, ML already you are aware of that, nothing to explain, right. Bit I'll talk little bit here again as a 3 machine learning algorithms you see here. One is called supervised machine learning algorithm, which already we had a emphasis on study class, but apart from the supervised we do also have called unsupervised machine learning algorithms which have a dimension reduction techniques. Then we have called clustering algorithm, right. So k-mean clustering is one such important method that used for in medical field as well. Dimension reduction technique is also used various methods in mainly used in high volume data. For example, whenever we have a hyperspectral data always contain a large volume of data, and some of the spectrum band may not be relevant. So we need to do a dimension reduction in the sense that we need to just take a most relevant bands which are having the rich information related to a specific application. Then third machine learning category is here called reinforcement machine learning, which basically started using in the gaming, then later on used in the other part of like robotics is one such field, and then real-time decision making, skill acquisitions. Apart from this, reinforcement also used in the chip design also, right, some applications, as well as in a autonomous vehicle what you see coming to the road, right. Even some started in the US, but still you see the India yet to come, right. So in the autonomous vehicle also that reinforcement algorithm also use that, right. This is very important. If you see that healthcare data what we have, the data normally is one dimensional data, 2-dimensional data, and 3D-dimensional data. All the data is captured from our human body, right. So if you see over here, this is the anatomy of the human body, and the focus if you see here like heart, liver, stomach, kidney, bladder, and then spleen, lungs, brain, and intestine, right. There are other parts also, but whatever the part listed here are the most important, right. That and the research whatever is around, right, most of these parts which is listed over here. So in this, the whatever the organ mentioned, so I would be focusing on the liver part, how the histopathology images will be used for liver cancer grading as well as the cancer grading, right. Cancer detection, then what kind of the liver cancer grade is there, whether grade 1, 2, 3, 4 like that, okay. And does not mean other part are not important, right. Even this is called bladder, here is called prostate. Prostate is one such common problem in a human, in a basically a male category, right? So prostate is again the early detection of the prostate cancer or the tumor is essential. For that, how histopathology could be used for doing such tasks. And recently our paper got published in the prostate cancer 2025 in biomedical signal processing and control as well, right? So if you're interested, you can read that. One more paper extension of this work is already revision, so you can see that. So our focus of histopathology mainly on the liver, breast, colon, and then this prostate, right? That there. So, and as I told you here, the data is 1D healthcare data. So the data will be captured from biological sensor, like as I told you yesterday also, ECG, EEG, EMG, right? Surface EMG and all. These are the one-dimensional signal data, right? One or broader 1D healthcare data. So then we have called 2D healthcare data. 2D healthcare data is nothing the image modalities like your ultrasound, MRI, CT scan, not X-ray basically, right? CT scan is 3D modalities, right, and so on, right? So 2D data format what are available like pathology images and so on. This your skin disease images, let's call dermoscopy images and so on. And then third 3D healthcare data, right? So just I will be summarizing just 5 to 10 minutes, get the glimpses what the data is there. You might be already aware of that. So this is how the ECG will capture. So here the devices at handheld devices, and you see the digital ECG waveform, you can get print as well. And this is how PQRS, I hope Professor already had talked about these things, right? And then you have EEG signals, right? In their different waves, different frequencies, right? And their behaviors, right? Then this is like different form of the ECG signals, normal, spikes, run, say and wave, the different stages. And this is how the ECG signal will capture in the hospitals. So like patient is sitting and then this doctor is just capturing, or maybe technician as well, the ECG of the patient, right? You can see that capturing device. Again, this also you can do handheld devices, right? Nowadays technology is very advanced. You need not to bother always. If not there, patient cannot go to hospital, right? Many hospital will come to you and take the data and get the test done at your home, on paid services, right? And most of this hospital are working in the similar the concepts. Just give the appointment, the person will come, collect your blood, and that report will come to your WhatsApp or your email in digital form, right? And then we have called EMG signals, surface signals, which here used for the the capturing with these are the electrodes, right? Surface electrodes putting and capturing the signals, and those signals could be used for the processing various tasks as well, right? This is the form of raw signals, and then rectification, filtering, and then finally the root mean square, the calculated house there for the EMG signals. Surface EMG, we had one paper this year basically from the surface EMGs are gesture recognitions, like from the surface EMG signals also. This is other called PCG data, and this called phonocardiogram signals that are very important for again the heart analysis. So PCG heart sound signals you can see over here, and more detail if you are interested, you can see the research paper for how PCG heart sounds will be used for heart diagnostic as well. This is all about the 1D digital data available. Then coming to your 2D medical data, I'll quickly. So X-ray, ultrasound, mammography, 2D echoes, these are the 2D image modalities which are used for various applications. Then we have a 3D, which is called CT scan. So CT scan was again very powerful during the COVID, right? It started. So if you get infected by the COVID, so either they are doing the X-ray if not visible, then they'll go for the CT scan. And then that was extensive use, CT score basically for the COVID infections right now. So COVID-19, COVID non-COVID-19, right? Detection was done using the that your CT scan as well, right? So both CT scan as well X-ray, right? Pneumonia test all could be done using these machines. Then coming to the MRI, so MRI again is very extensive use of the scan, right? For any organ, but most frequently used for the brain or maybe some spine case as well. So you see the different plane, axial plane, sagittal plane, and then coronal plane. So this is a machine, you have seen that. I also have gone to find this spinal cord once, right? So very painful, very sound, very irritating sounds come in the machine, right? And other interesting development happen in the field of MRI, that's called low dose this MRI machines. So this is a low dose MRI machines. Basically it's a Siemens recently introduced this machine, and here it had capability of scanning the complete body, your human body. Can be like, here you see that, lie on the bed, the whole body will be scanned, right? This is very important for us, like cystic fibrosis analysis, pulmonary hypertension, heart failure, COVID-19, any other disease. Why this is low dose MRI is more powerful? Because for the smaller kids, you cannot put the kids, children's for the machine again, right? Because the current that whatever there in India, all machines are the high dose MRI machines. So if this low dose MRI machine will be deployed in the hospital, so like if in the heart case, like this angioplasty surgery, right? So angiography is very painful, right? You have to put wire through, they'll put and then put stent, all the things, right? And they also, if you want to see, they have to put still that camera, minute camera through the nerves goes, right? Heart, right? Case. So instead of, and it's very painful, right? Instead of putting the, going this invasive method, if you go for non-invasives, it will be much easier, right? Now, so this is again powerful, that will help for this cardiac analysis, right? Like heart, like if minor heart attack is there, so that you can see any blockage is there, that everything can be seen in these machines. Very good machines, but not yet available all hospital, only right few hospitals is available in the US only. But it would be good to have all hospital this kind of machines, low dose machines, MRI. Then other we have called PET machines, you have seen, right? So PET is again scan is very important, especially whenever you have like in a woman's, right, like breast cancer. So breast cancer mammography when failed will not give you doctor is in dilemma, right? Is there, not there, right? Not confirmed. Then what they'll go for higher level of scan, that's called PET scan. So in PET scan you can see that very clearly, that like there is a breast cancer is there or tumor is there, all things you can do more better way in the is PET machine. And then the chemography, this radiation PET, that's all that treatment will start that, okay? So you can see that this is a PET image and this is MRI, and then this is called fusion basically, that's called multimodal fusion analysis, right? So here you see that individual both are not enough for the radiologist or the oncologist to take decisions. So what they'll do, for the same patient, they will scan PET images as MRI and then try to do the fusion part, right? And then after you see the fuse quality, fuse image data would be much better than the individual scans. For me, I have seen practically in the hospital in oncology department, KMC, Mangalore, because my the HOD was the close friend, collaborators, Dr. Piyush Saxena. So I visited and see how they are doing the fusion for even for breast cancer diagnostic as well, right? So they also do the fusions. And then likewise, other is called a SPECT, also used for scanning. So we have called this machine SPECT, and this is called low contrast, MRI. MRI, T1, T2, T3, different contrasts are there. And individually, if you see that the scan is not enough to take a diagnostic decision, but if you see that the fuse data, fuse image is much clearer than the both individual images, right? That's what the radiologists and oncologists they will use that, right? Depending on their what kind of the disease they are looking at. Okay. And this is like some machines which also is there called PET and SPECT together like this. And we have also called 3D ultrasound, right? So 3D ultrasounds is nothing like 3D echoes. So before going to angiography right now, so they'll also see this is called 3D echography, right? So in this case you can see the color, basically the Doppler test you see, you know that, right? In nothing 3D echography, right? So the pictures will be more clear and that can be used. That likewise this complete machine, and this is how the image is there and could be used for various diagnostic decisions also for early detection as well, right? See that is there or not, right? Then we have called 2D further digital imaging also called endoscopy. Endoscopy actually you will get the 3D image, that's you will videos frame by frame, but frame is nothing is image. So you can get the images. This is how the capsule that goes to your stomach and keep on sending the signals, right? Now, maybe 25 frame per second or maybe even more as well, right? So, and this is how before that will happen, and then when it goes inside this capsule, right? And this is how you see the images, like different forms, and these are the like different conditions. See your inside stomach, right? It's scaring actually. Some of the images are very scary right now. If you see that, right? If you not seen, you are very happy. But if you see that, you feel your tension is started. That happened. Then apart from that, we have called 2D more digital images called retinal images. So retinal images again we have called, this is scan. I hope everyone gone for eye testing, right? So first they have put it, fundus camera, right? And then called OCT, optical tomography. These two are the retinal images scans, right? So here this is top is called fundus images, camera will be used, and bottom is called the OCT, optical tomography will be used for the retinal the scans right now. And sometime like you have a diabetic right now. So diabetic case also these images will help us to scan as well. Apart from your HbA1c, right, is one such measure for glucose, sugar, right? But that if you see that retina also get damaged, right? So their vessels, retina vessels get damaged as well, right? Then moving like in dermoscopy field, skin specialist, right, department. So various skin diseases, right? This handle device, you get the images, right? And you can see that what kind of, basically you have melanoma disease is there or not by looking that this can be done right now. Moving toward on 2D digital pathology, this is my core research. Last I would say that 2017 we are working deeply on this field in digital pathology. So this is a complete setup of how we'll get the digital pathology image. This is called a specimen, a small infected organ of the human body, get cut it, which will be millimeter, and then from that they will prepare the glass slides, specimen, glass slide. How glass slide will be going to prepare? There is a slides is there. I'll come back later on. Complete setup is there. So glass slide, and then once glass slide is ready, and it's not a straightforward method, right? Now, lot of steps are there to making glass slides, and one way you can use microscopy, right? In my lab is there microscopy, is there pathology microscopy first floor. If you want, you can see that as a picture, right? Physically, and you can put this RY over here, and this give you as a one region of interest. You can scan that, and also this called slide scanner, right? So the digital slide scanner, this is called digital slide scanner, which is called 3D Histech from is available. I'll come back. There are a lot of slides are there, but in general this is called slide scanner. Slide scanner in the sense that this whole slide, if you see there's a place here over here, you need to just insert that inside slide, and then whole slide get scanned, and the scan image will be called like this, and the name we call as a whole slide imaging, WSI, right? And the size of this image will be in the GB. It may be 2 GB, right, or maybe 1.5 GB or 1 GB, depend on the slides here, but it will be high. If you have one slide, one patient, right, if you have 100 patient, right, data, so what will be the amount of data you are going to generate right now? So if you have 100 into 1.5 GB, so this much data will be there, and to work on that, high volume data, again you require the very high computing facility, right? So your normal workstation is not enough. You have to go for cloud computing, right? Or you have server, you have to make that, right? Rack server and all the things will be required that, okay? I hope that makes sense, right? And this is image actually, right? Pathology image, right? So what we'll do from this also, if you don't have computing, what you can do? You can get small patches from this whole slide imaging, right? That's called patch based processing right now. Okay, now the research is almost stopped on the patch base. Now the current research going on only doing analysis on this whole slide imaging, right? So this was the that histopathology images. So if you look at in this image, two things are important. One is called nuclei. Nuclei, whatever the blue color you see that, no, this is nothing the nuclei, which is the interest of the objects, and rest all be called cytoplasm, right? And for healthy tissue, right, the shape, size and color will be normal, but if unhealthy tissue organ, then get changed. Color will get dark blue, right now, color will change, shape will change, size will change. So everything gets changed right now. That means in simple word, the textural property of the complete image will be different for the cancerous organ, right? So in general, if you say histopathology, this is standard definition. Histopathology is the diagnosis and a study of a disease of the tissue under microscopy, right? Standard definition, old definitions, right? But now this definition is changed, because we are going for automations right now. So to do analysis for pathologist grading, one pathologist you have to wait for 1 week. A moment a specimen is taken in the hospital and getting the report, this time duration is 1 week time, because everything is manual, right? So what is the role of AI and deep learning is that at least the role of AI, this will be always there, right? So instead of doing the analysis grading manually with the naked eyes, pathologists, which they have to spend 2 days, 2 and 3 days to just see that each and every small region of interest need to see, zoom in the microscopy and see that, right? Instead of that, once this is ready, right, put it into the automation system, right, AI based solution system, right, which can give you the direct solutions. That WSI image, right, is a cancerous or non-cancerous. If a cancerous, again what level of cancer is there, whether grade 1, grade 2, grade 3, grade 4, right? So this is same things, and this very for in any all clinical, see anything for as far as tumor is concerned, or the tumor, again tumor may be cancerous, may not be cancerous, both possibilities there. If non-cancerous, very good news. If tumor remove, fine, patient will be alright. But if it become cancerous tumor, then problem is started. Then life is a threatening will happen, right? So it's just like all the cases to get confirmed whether tumor is a cancer or non-cancerous, they have to go for biopsy, right? Take them and put the laboratory and get the opinion of pathologist whether this tumor is a cancerous or non-cancerous, right? That will be done by pathologist only, okay? And this is other part is called cytopathology image. Cytopathology image, this is generated from the RBC, the blood, whatever you give it in the laboratory. do not require any kind of specimen infected organ, right? So like various like WC analysis, various other tests, right, done through your RBC. For that also, like if like urine infection is there, right now. So urine infected case, you don't require cut in this part, right now. So you can use the the test, laboratory test data and can do the analysis as well, right? Now coming to the teaching machine to interpret medical data, right? Very important, simple and important concept, right? So here, in a simple word, to make you understand, this picture already you have seen that, okay? So this input what we see as a human image, but computer will see the numbers, right? Same way, this is we have, let's say, MRI image, okay? This MRI image, right, which has 3 channels, red, green and blue, right? Okay? So these channels here, if you see particular over here, 34 number, this number is 34, right? But actually is the binary, right? If you see this number representation, when you store that, right, that it has to be digital number to convert it, right? So if you want to read, right, how machine will read? Machine will understand the numbers only, right? So let's we have a data, medical data, then we call algorithm, certain algorithm do, and then detecting tumor whether cancerous or non-cancerous, right? Okay. For example, picture visualization. This is image, MRI image. What is the algorithm? Predicted as a tumor, right? Again, if tumor, what kind of the tumor level is there, right? Okay. Further, you can do that. Like here, the medical. Further, normal, grade 1, grade 2, grade 3, grade 4. If it's cancerous, very dangerous tumor, right? So you have to further classify that, okay? Grade 1, grade 2, grade 3. This complete talk about the here. So we have called data analyst and medical expert and then medical clinical domains, right? So if we want a robust system, right? So doctor and then AI specialist both has to work together. Until both work together, right, a good solutions will not be come out. Why India is lagging? Because of one reasons. In India, major problem is that doctors and engineers are not together. Here medical college separate, engineering are separate. IIT is different, IIMs is different. Why not in the same campus? If it would be same campus, IIT and IIMs together, right, then the research product would be different, label will be different. That's one biggest problem in India, right? I have struggled to get the data because I know how to get the data from that, how to get opinion, all things are not very easy, right, in India, right, specifically. So role of the data scientist is to develop AI algorithm, do some sort of analysis, pre-processing, right, and then AI system, but ultimately the result has to be validated by the medical expert, right? Because he has to accept whether this the result of the algorithm is acceptable by the doctor entity or not, right? So medical expert is important. So like this clinical domain which doctor is having, right, and then data analyst to all kind of development analysis, algorithm development, testing, and then like system, data and visualization, like computer based diagnosis system, right? So everyone has to work together. That's called human analytic computer ML interpretability cycle through interactive visualization. So if we over the time when work together, maybe the dependency on the 100% doctor can be minimized, right? Various tasks, various analysis could be done by the AI system. AI will assist the doctor, will not be replace the doctor, but it assists that how to do quick diagnostic decisions, right? And the doctor can validate quickly. Yes, whenever there is a doubtful, then he can do second opinion, right, by setting whenever he is having time that, okay? And also, since we are digital era, if this doctor is free, the data can be saved to the cloud, report everything to the person who is sitting in the Delhi. He can give opinions. Nothing wrong, right? Patient is not going to Delhi. Only the data will go to Delhi through cloud. So things are possible, everything through cloud based. So again, you see here this particular image, MRI image and tumor detected. So the A figure is a brain images without tumor, and then bottom B figure is here brain images with the tumor here, right? So you see the mark regions here is nothing, these are the tumor regions are there, right? Then if again tumor is there, again brain tumor, there are different classes are there, right? So could be a 15 classes brain tumor classification, 40 class tumor classification, 4 class tumor, 9 class tumor classifications can be done, right? So here you see that just 3 classes, right? A is melanoma, brain tumor, glaucoma, and pituitary brain tumor. So 3 class of the brain tumor you will mark over here, right? Likewise, the data is there. If you Google it in Kaggle, right, you can get data. 9 class brain tumor classification, 15 class brain tumor classification, and your even 44 class brain tumor classification data is available. Data is not a problem now. Data is almost every field is available. Problem is patience, sit, spend time and develop a best AI algorithms for diagnostic solutions, right? For diagnostic purpose, for detecting that. Again here, like brain tumor detections. So see, these are the tumor images, and then B part and is your ground truth, and D part is printed by the algorithms, right? And this guy has worked on, and if you people read this paper, optimized brain tumor detection, a dual mode approach for MRI image enhancement and tumor classifications. So you can see that here, right? Tumor can be detected as a segmentation task. I hope professor has already told the image segmentation little bit in a medical field, right? Then in a retinal, you have seen the retinal images in the beginning, right? In my introductory slides. So here also, if we have retinal images also, AI based system, AI based solutions will help you to detect different type of retinal diseases, right? What are the retinal diseases are there? So these are the different categories, right? Here mentions all the retinal diseases types are available, right? Here just few are listed in your fundus images, right? Okay, and this also is camera is a portable camera, right? Is there right now fundus, right? You can port and get capture images as well. More information you can read this paper, get like retinal disease detections in 2022. All these are the classes of diabetic retinopathy, normal, media haze, ODS, optic disc cupping. I mean, myopia is common retinal disease, right? So all classes are listed over here, age-related disease, everything you can do that, right? Do the classification. So AI-based help us what? Even you have solutions, these are the fundus camera images is good, right? In ophthalmology department, AI-based, right? If you go there, put your images, things will happen. Wait for more time, right? That's called AI hospital, right? Where you go there, every test will be done. I think I saw that if you go there in that AI health booth, right? Recently I read that. If you go there inside the booth, right? It will tell your BP, blood sugar, some basic tests, right? Easily get extracted and get reported. Yes, everything is normal, right? If some problem, then only you need to visit hospital, right? So that's possibility is there. This is again, your OCT, optical tomography images. So retinal diseases. So here you see there are 4 only classes listed here: CNV, DME, Trosen, and normal images. So for that, deep learning AI-based solutions will help us to detecting the retinal diseases. And this is what the machine, right? Scanner OCT scan by this German machines use almost every hospital. So in a retina case, there is a limited, most of the machines come from the Germany only, right? As far technology is concerned, they are good in that. They are good in optics actually. Germany is known for optics, right? Then coming to the digital pathology. So digital pathology, Question is why need of digital pathology? So one thing is improved workflow in the laboratory, in the sense that, right, the slides can be when we have digital slides, so that digital slides, right, can be shared to the other hospitals, right, can be shared to the other city like in Delhi, right, or Bangalore, right. If some very good specialist is there, just send this slides to the other specialists and get opinion pathologists, right. So that's called workflow can be shared across the site and labs. So like KMC itself have a different labs, right, different pathologists are there. So if the lab is available in Bangalore and a specialist is sitting over here, so maybe the same the report like digital slide can be shared to the Bangalore specialist. Possibility is there because all are connected through the network through clouds, right. Extension and reorganization of the sub-specialty reporting. When digital is there, reporting is easy. Nowadays KMC is very good, right. Yeah, all the reports, scans, they are keeping for 1 week in the server. You can download, keep it safe places for your reference, right. Potential solutions for local shortage of pathologists. Yes, I told you. Especially when the rurals, none of the doctor want to go and serve in the rural, right. But if we create a good facility in the rural, like we can have lab there, all the facility and scan done there, and everything should be shared to the cloud to the doctor who is sitting in the metro. So patient need not to travel 200 kilometer city, right. Everything can be done nearby district hospitals. In that case, government, state government, if we create very good this facility, lab facility in the primary health care center in almost every district is there, right now, right, and that will be connected with the like one metro hospitals, big collaborations, very good taking care will happen right now. That will happen easily. Early disease, this disease detection will be possible with the help of government support and this even the big hospital supports as well, right. So making easier to share the case between the multiple pathologists, right, is will be there. And second opinion can be sought, which may help to improve the overall quality of the healthcare service. Is very important. Never ever rely, right, opinion of a single doctor when it comes to the health, right. Always take the second opinion or third opinions, right. For the same case, the diagnostics, two doctors may have different opinion, right. If two are there, if work is still not there, take the third. 3 opinion medical experts, and 3 which is common, you go with that, right. If 2 say that yes, no need of any surgery, yes, no need of surgery, you go with the medicines only, right. If one say that no, procedure is required, option required, don't listen. That guy may not be have their some other agendas, okay. So always, and don't rely the single laboratory report as well, right. Take that lab test with the other lab as well, right now. Because sometime if you are frequent visitor in the same lab, they have all the records are available in their database. They may forget to change also, right now. That may happen because it's not only your single report. They have to do sometime 100, 200 reporting they have to do. They are human ultimately who make the reports, right. Possibilities there. So don't believe in a single test. Okay, this is my just advice as a little bit experience in the little bit in the domain, right. Then other advantage of digital pathology over here is portability, ease of sharing, retrieval of archival images, ability to make the computer aided diagnostic tool very easily. When we have a large data like historical data of a particular disease, it's good to strengthen the computer based solutions, AI based solutions, right. Because if you want to build a AI based solutions, you need large amount of data, and data only possible, and data cannot be shared just like that patient, right. It's ethical things, right. So before the sharing hospital data to the researcher, they have to take patient consent. Without patient consent, the hospital doesn't have right to share data for research purpose. That's make sure that, okay, that's very important. Now ethical clearance is very important, right? I haven't come to the patient data. Increase productivity, of course. When you have the data, archive data is there, that will help to build better AI based solutions, and then you can, and also if you are keeping archive data, if your model is not very good, maybe after a few years you can redevelop it, retrain, redevelop, redesign that, right? So that the scalability, right, or the robustness of the model will increase in future as well. Okay, so archiving of the data is very much essential. Unless you tell the doctor, I need data after 1 year, they'll not procuring, they'll not take the consent, patient consent. Okay, that's very important. Then why use digital slides? Again, very important. Education, classroom teaching, this be used. Research and pharma, they will also can. Publication, telepathology, teleconsultation is important, and then your primary diagnosis, right? So these are the advantages of digital pathologies, right? Digital pathology, digital slides, right? This is a complete, radiology. If you see, patient, scan, fill, radiologies, right? Now tissue, lab, slide, and pathologies. This is called pathology, this is called radiology, right? In this pathology, these are the complete procedures which a pathologist has to do. Pathologist technician has to do that, right? You start from tissue collection, and pathology they will not do this tissue collections. The tissue has to be cut by the specific department. Like if skin, any infected skin is there, so skin department they could take it out small millimeter tissue or infected organ. Likewise, if like say for oncology department they will do, or like any radiology department they can do also, right? They can also cut radiologists, right? They have instrument is there, right? Everyone cannot do that, needs a specialized instrument that for doing that. So tissue, once they receive the tissue, right, in packed form, sealed, right, then they do the fixation. So from here the pathology task. Fixation, they have to put glass slide, the embedding, sectioning, deferrifying, staining. Staining they have to do, get called hematoxin and eosin. Then you see the color, whatever is that image pathology you have seen. Digital pathology, because of this color comes from this staining only, right? And this should be correct. This may be, if this is not correct, the pathology, the image will not be correct. So the staining should be proper, and then finally glass slide will be ready, which you have seen this, right? This is a complete procedure done by the pathology lab. Of course, pathologist will not do this part. Their lab technician will be doing this part, right? Under the supervision of pathologist only, right? This already you have seen. So these are the types of digital slide scanner. So Olympus, Nikon, Zeiss, Hamamatsu. Hamamatsu is very good, which comes from Japan. And 3D Histech, and then Aperio. Aperio is there somewhere. Where is this? It is. This comes from I think this Finland, this Aperio. Aperio is very good, slide scanner. But it is costly. I work on this Hamamatsu and this 3D Histech in Japan when I was there as a visiting scientist over there for 2 weeks. So I was using these 2 machines for scanning purpose, right? And of course, even they are Indian also, they have developed the whole slide scanner as well right now. So this is the view, right? Hamamatsu, this scan, right? That's called NDP, right? So this is the complete. You see the image right here. So very good scanner, fast and automated scanning, high resolutions up to 0.23 micrometer per pixels. So you can think that a very high resolution image, right? And magnification, right? This comes like software also comes for that. You have to install that. Nano zoomer, right? You can install that. 20 to 40x magnification factor, means you can zoom in, zoom out, right? Now option is there, right? You can see that. So pathologists also they'll do, right? When they do any other microscopy like Olympus, all things, right? They have to also, they have facility to zoom that, right? Select the RY and you can zoom that, okay? This is called aperio, very good. So if you see here these things, what you see, these are the basically the racks. So you can put, multiple slides over here and you can scan that, right? Looks like here it though. Aperio CS2 is very high quality digital slide scanner. Easily load and scan up to 5 slides. You can put a 5 slide for scanning, right? And this also have 20-40x magnification factor, right? High capacity scanner called Aperio A2 and Aperio GT40. These are the highest capacity scanner, right? But this is basically that is good for research point of view. You can do that. This is other called 3D Histech, right? Which in the beginning you have seen my slides, This is here the region which you have to put the scanner, right? And you can get the image, you can take the RY and do whatever want task, you can do that as well, right? And this other light Focus 20 portable WSI scanner, and you see that this complete way here, right? All the part, if you see that is scanning all the things like full metal design, this region. This is just overview of the, again is scanner, right? Light scanner, right? So again, that capabilities, right, will vary based on the different scanner, right? Quality and everything that whole slide scanner or microscope depend on the optics. What kind of the sensor they have used? Optical sensor, right? Optics, right? That's used. If you have very high good optics, you'll get very high good quality of optical image, this pathology image. So maybe a bright field or fluorescence, both are there, or maybe both, right? Normally you'll get bright field, this microscope will see that, right? Capability vary from 1 slide to 400 or more slides. You can do a scan at a time, right? Then you have called various slide handling mechanisms, like we have single plane scan or maybe JUT, stacking also possible, software feature and so on, right? Slide scanning methods, focusing methods, everything get changed. I'm not going to deeper that part. If you read that, how that technical more happen as a development of this, microscopy, you will come to know what kind of things happen. I hope, is there any questions over here till that, what you have seen that? I hope it's in basic things, but it's very important to know as well, right?
I would like to confirm that Aperio and Leica is the same, because I got to know that Aperio is now under Leica.
Maybe it's acquire that, if company Leica, yes, Aperio is the the Leica is a company who is manufacturing this Aperio slide scanner. Leica is a company, yes. Okay, yeah, that's correct only, right? I did not put here the company names, right? Who is what factory? Just as a brand, like Aperio is a name of one particular scanner, but Leica is a company, right? Which manufacturing this scanner, right? Now it's easy to put in Google, you can get details, right? Not a problem. So this part already I discussed, last class, right? I'll skip. So now I'm just moving ahead for that. So this linear architecture study I have explained you, right? That 5 layer architectures, 3 convolution layer, 2 weighted layer, or 2 convolution layer, 3 weighted layer. You can choose as per your convenience. Then AlexNet, which is basically 8 weighted layer architectures, VG16, 19, 16 weighted layer architectures, Google Net, Inception Net. Finally, this I want to later on. And ResNet is a more powerful architectures as a deep learning architectures, right? So ResNet 50 is one such which used for various applications as well. Likewise, DenseNet, Inception ResNet, right? And so on, right? And then you can come up with your own model as well, right? So this is a linear model 5. Need not to explain again. This is AlexNet model, right? So AlexNet, if you see here the flow, we have input data, right? And then convolution, then get the feature map, max pooling, then conclusion, again get the feature map like this here. So see here, kernel size is here 11 cross 11, here kernel size 5 cross 5, here this convolution kernel size 3 cross 3, right? Okay, that means there is a different type of the kernel sizes, right? Now there is no uniformity, right? Number one. Second is that here pooling size and is tied. If you see is tied 4 here, see here is tied 1. If not mentioned means 1, right? Here is 1. So different type of style use. Okay, there are 2 things, observations, and here using 3 consecutive convolution layers, right? Now, and finally you get what? There is a fully connected layer, and this is a 101 nodes softmax, because the model was the winner in the challenge, right? ISLBCC challenge, okay, which is the challenge. It started in 2012 only, right? But this is as a breakthrough start from here only, right? When Alexa models, and then after that, now the research is started, everyone starting modifying and so on. And this is a color image, and here the kernel size 11, then 5 and 3, 3, right? Finally you see that you will get the flattening, then this layer, right? Now this application you have seen that already discussed. In a broader sense, in a healthcare, we'll have called pre-processing of medical data. For pre-processing also you can use AI, deep learning algorithms. Single object segmentation from medical data, that's basically used for as a brain tumor segmentation task, right? You can do that. Or you have called retina basal segmentation you can do, or multiple object segmentation from the medical data, like heart chamber segmentations is one such, and then in a histopathology called multiple nuclear segmentation also can be do. Likewise other applications also can be explored. Then called CAD system classification of tumor, not tumor from the medical data, medical images. Then called classification of subtype of cancer image from medical data. So these are the 3 broader core application in the healthcare data, right? Irrespective of medical imaging, right? It may be CT scan, MRI, ultrasound, retina, whatever is there, right? You will be doing 3 tasks: regression, right? And regression or classification broader sense, right? Now, so classification you can divide into further 2 types, which we call as a one is called image based, number 1. Second is called pixel based. Image based classification. Image based classification means the whole patch, this is called image, right? But you treat it as a patch. This patch or image, right, belongs to either normal image, or maybe a like grade 1 or grade 2 or grade 3, right, or grade 4, right? That makes sense, right? Image or the patch belongs to any one particular class, right? Now, okay, so that means this image is nothing. These are intensity values, right, or called pixel values, okay. So the whole image, the intensity value will be same, right? All the intensity value belongs to one particular class, either normal or the grade 1 or grade 2 or grade 3 or grade 4. That makes sense, okay. Now in case of the pixel based classification, right, so set of pixels, this is your, let's say, patch image. This may be your, let's 512 cross 512 image. This also is 512 cross 512 image. Okay, both are the same size. Now here you have seen that one tumor image, right? Tumor detector, right? Now, so in the entire image, one possibility is there. This is the one mark region. So whatever region is represented, these are nothing, these are the sum. In my terminology, these are the nuclei I will call, okay? Nuclei detected, shaded regions in histopathology image, correct? So these are the, will be whiter region, mark regions, is the nuclei, rest is a black regions, right? Okay? So I am just looking the nuclei detection as a task, right? So this, wherever is the white regions, right, there will be a same intensity value, same pixel value, okay, and wherever is a black will be like, as you know, 0, right? So in this image you have only two intensity value, right? 0 and 1 means 255, right? Okay, so two intensity value, but that may also possible when you go for like one class, like heart chamber segmentation, if you are doing that, okay? Okay, so you may have left, right, three regions will be there, this one regions, and similarly the left and right both the cases. So this have the so now three colors will be representation, right? One is a background, this represent different color, this represent different color, right? So how three colors that represent the three different intensity values, okay? So what is the difference here is that set of pixel belongs to a particular class, right? Now zeros pixel set of pixels is one class, white set of pixel belongs to other class, right? And that's we have green color belongs to other class, right? So set of pixel is belongs to represent a particular class. That's called pixel based classification, right? That makes sense, right? So segmentation is nothing, is a pixel based classification, right? And cancer grading is nothing, right? It's a image based classification or patch based classification, right? So again, all the applications, you know, regression, binary classification, all things, this already we had discussed yesterday, right? It has few real, you know, application from the medical data. So here called one is a multi-model medical fusion as a regression task, right? Then bone age estimation from hand X-ray image you can do. Lung age estimation from the CT scan, that's again regression task. Brain age estimation from the MRI scan, that's possible. De-speckling of ultrasound image, medical image in general, but ultrasound and your OCT, de-speckling is most important task will be done, right? Contrast enhancement medical image again a regression task, right? So these are the set of real medical data where you need to do some sort of as regression task. For that you need to build AI algorithm, deep learning algorithm for doing this task. Otherwise done by the traditional methods, right? You have already seen that, okay? But taught by professor also, okay? So this is one example of doing the multi-model medical fusion. So we have CT scan, we have MRI, and this you see that different methods start from here, right? There are different methods, right? And this is what the author, the link, right, from where this the images comes from there. So this result is a author work, right here, FWNet, right? This author work, this paper, right? And he has compared with the various existing algorithm. These are the non-deep learning algorithm. This was non-deep learning method. This was non-deep learning based. Some are non-deep learning, some are this year I think Gabor filter use, right? So he has compared nicely extensive comparison and then compared that. So individual, right, images are not enough for taking any diagnostic decision. So the fusion is must, right? You can do. Likewise, you see that already you have seen such image. The source is here. Low contrast MRI, SPECT, and this is your fuse image, right? For that also you can build deep learning algorithm for that. And then PET, fusion of PET and MRI images, you can see. This is PET image, this is MRI, and this is your fused image, right? So fused image is much better than the individual image, right? For this task also you can use that as well. This is a complete set of age estimation from the X-ray images. We have worked on the bone age estimation from the X-ray images without using deep learning, and then and we have created data set as well from the hospital, from the Goa, right? GC Medical College Goa, from that, and nowadays many authors, they have extended work using the deep learning also, right? So you can use deep learning for the bone age estimation or age estimation in general as well, right? So, and also can be used from the age estimation from the X-ray image also. So from like X-ray, this complete setup here, you see that DL models, training, all things, and then your transfer learning approach also used, and then validation tests, all the steps, and then can be used for. This is, if you are interested, deep learning based age estimation from chest X-ray, right, indicates the cardiovascular prognosis also, right? You can refer the paper and you get the idea as well, right? Then you can do for age estimation the same way in broader sense, CT scan image, right? Also, you can use X-ray, you can use CT scan also, right? So do some pre-processing, then use the method, then your inception regent models, and then finally you can get the CT age. So CT age, what is CT age? What is the actual age, right? So if healthy person, his CT age will be more, I mean good. But if someone whose lung is weak, right, due to any disease, then this CT age will be reduced, that, right? Now, when CT age reduced, that means the person is suffering from some maybe infected, maybe pneumonia or some other, or COVID also, right? In COVID case, that lung, that CT age will be different, right? So it may improve further the medications are as well, right? Likewise, you can do a brain age estimation. Brain case, you will not give you exact, the age, but give you the range of the age, right? Now, for example, the data set already there. If you are interested, read this paper, right, and get the input data, 3D volume of label corresponding, accept 2D Excel slices, use the retrain resident 18 model, and classify the age group of a persons, right? Like age 3 to 5, with 7 to 12, or adults here, right?
Ground truth label is what?
Ground truth label means like that by doctors they have to do, right? Now, labeling has to be done by the doctors. This is age group 3 to 5 range, right? For healthy person, what is the age, right? What is the age? You have to create the data, and then for non-healthy case. So actually, and once is the age is their birth age, right? Now, so like many people who are having brain abnormalities, right? Now, brain problems, their age will not be like their actual age, birth age, right? There will be difference. So that estimations can be done from this MRI data also, right? Now this is what this guy was talking on this. You can read and get idea about this. This also talk about this accurate brain age prediction with a lightweight deep learning network by these guys. 2021, you can refer that, right? The data is already available. This, right? You can get and you can extend the work if you have some interest on that, right? And then other is called de-speckling of medical ultrasound image. So many guys have worked on that de-speckling for that minimization of speckle noise, right? So for that also you can use deep learning models you can design. This is one model which was done by these guys, okay, Ankur et al. For de-speckling of the ultrasound images. So noisy image and then get the de-noise image, right? This is complete architecture. And in a histopathology we use called color normalization, right? So color normalization is very important because from the one scanner other scanner there is a difference, variations will be there. So you need to do some sort of color normalizations. For that you can build AI based solutions, or you can use stain normalization. For that also you can be used deep learning algorithms as well, right? So this is a target image, this is a source image. So here the color texture will be remain same, but the color has to transfer here. So if you see that here, texture remains same, but the color is transferred from here. Likewise here, source, other source image, like this here, right? You can see that. The texture remain retained. Texture should not be changed. Only the colors need to be transferred. What the pathologic color wanted right now. This is called color normalization.
Sponge color or color of what? Sponge color?
No, this is the good quality of the pathology image color right now. Like nuclear color, cytoplasm color, that has to be their good quality. So basically from that we are transferring the color of the nuclear, color of the cytoplasm, right? That's what color means. Nuclear and cytoplasm color has to be transferred by retaining the texture, right? Okay. And because the color variations may be happen due to the sensor itself, optical sensor what you use. So to overcome the limitations you can use that, right? And this is already applications, building that, which already we discussed previous class. If you're building the deep learning models, of course activation should be used linear. This better way you can do. Activation linear, loss function MSC, right? Optimizer anyone you can use, SGD, ADAM and so on. Output layer you have to use linear activations. This is one such example of, as a next binary classification. So binary classification already we have seen. This is one example if you see, right? Blue color data belongs to one class and yellow color data belongs to your second class, one class, right? 0 and 1 class classification as a binary classification. These are the various examples in medical field, right? You can explore. This is one such illustrations of this, like nuclear segmentation. You see, this is our paper. And this is a very good citation we received in very less time, 2021 published. Data is also released publicly, right? Code is also released publicly.
People ask some data source and other things. It's publicly available.
Yes. You can see if you visit my GitHub link, everything is there over. Completely open source, right? No worry for that. This multi-organ data set. This data set was different actually, but we have also called liver cancer data set, right? So we have multiple data set to use that. This is only for kidney histopathology data use. This is not our data. This is from other public data set is there. If you read paper, you can get that. So ground tooth, these are the detected. I have ground tooth overlay on the input data, and these are your detected nuclei. These are the set of these images. Ground tooth, corresponding unit model and attention unit model just for visualization. And you have seen for MRI, this task also you can do for brain tumor detection. For that you can do that. As a pixel based classification, you can do your image based classification task, right? Now, like COVID, non-COVID, right? This was shifted back. All the things you have seen that implementations, these steps. Binary cross entropy study discuss this part. Coming again that part, fine. So now other is called multi-class classification. So multi-class classification case, this is one such example which we have called 0, color, yellow and green. So this will talk about the 3 classes, right? 1 to 3 classes. There are other classes you can do like subtype of cancer detection, breast cancer, liver clone, kidney and so on, and other applications which may not be relevant for medical field. But you can get idea, right? It's not only healthcare, in other field also you can do many things, right? But this dedicated in the histopathology images called breast cancer grading. Benign and malignant. Benign have 4 subclasses, right? There correspond accuracy, recall, precision, and then you have called average accuracy on the benign. Similarly, the 4 subclasses are malignant, and you can see their accuracy, recall, precision and average 96. If you look at this, there is a still scope of improvement of the result by designing a better deep learning model. And this result was this model called BreastNet model, and the data set they have used called BRACHIS is publicly available, Brazil data set. You can download, and this is, I would say, is the first data set which was released in 2016 for larger volume of data. So everyone who started this field, the research in the histopathology, started from the first breast. So IIT Guwahati, there is a called Chandan, Dr. Chandan in Medical School of Technology. Right, in India he is the first that lab started. Then second is Amit Sethi, IIT Guwahati started, and third we started as a engineering domain from NIDK, and we started working on the liver cancer, right? Liver, then kidney, colon, prostate, and so on, right? So sufficient research has been conducted, right, in the field. Now lot of research are working in this histopathology in different cancer grading or detection as well right now. So this is called BRCHIS, is a popular data set freely available, right? Then you can do also, as you have seen the image, as a multi-class classification you can do, right? You can do multi-class nuclear segmentation, right? As I was telling that, you see that this is called gland, like colon part, right? These are benign, these are malignant case, right? See, as a part of multi-class segmentation, right? So these are touching regions, so you see treated as a one particular gland, right? Now, and this is here, you see that here, right? Where is the touching part? You see that, right? So touching gland treated as a single gland, right? Which is not correct, right? So you mark this yellow, this arrow represent that this is a touching part, that's why treated as a single gland, right? These are benign, these are malignant glands case, right? Organ. So later on the authors, Hao Chen et al., they have used called contour based network design, and you see that their results, right, is quite promising result, right? So you see there is no touching part here, right? So that's why this is separate gland, this is separate gland. Where these were touching in the yellow color, now see there is two are segregated, right? So idea of the segmentation histopathology is to segregating the touching nuclei, touching glands, and so on, right now. And like if you see that in case of malignant also same, here touching, but here see that segregated that, right? Here touching, here these are segregated that, right? So very important as a segmentation task, right? Multi-class segmentation with pixel based approach is also very important in the medical field, right? Likewise other heart chamber segmentation, my paper is there, you can read that, right? That also you see that how you use that. So this was the implementation step. If you go for that as a Python base, right, you can implement that. For that you can do that part, like already discussed, you have seen that. So coming to the available open source data set, so like histopathology segmentation data set available, you can see that. KMC level data set available my GitHub page, right? You just link it over here, Google that, you get that, right? And lots of codes, almost all my paper codes are available, right, on my GitHub page. You can download that data codes, right, whatever help needed we can support. And happy to say that this was the first paper, but later on we have also created grading part, right? In the GitHub my link is there, liver cancer grading data set. But there are other medical data set, right, in like endoscopy, artifacts detection, segmentation, disease detection, and then age-related molecular degenerations, cell tracking, diabetic retinopathy, right? All the links, if you visit, you can get the data set, right? Apart from this, if you Google it, called Google Research Data Set. Google is a one such, like Arabian Sea, right? We have Arabian Sea here, like Google is like Arabian Sea, right? Any data you want, just Google there, right? What if you know the data name, just Google, it will give you the link and will take you the right, path, give you the positions wherever the data is hosted. Apart from the Google research, like, Mendeley is there, Jodo is there, Kaggle is there, right? So these are the things you did. Just Google what you want, alright? What task you want, you'll get the data, right? Data is not a problem, right? Ultrasound, nerve segmentation, you get the data. Brain tumor, you can, the BRATS 15, 16, 17, lot of data is there, detections. And then LLG, low grade glaucoma segmentation data is there, right? Now you can get that. And all the COVID segmentation, you can get the data. So this link is there, right? You can get the data, that is not a problem. Here see the most of this Kaggle, right? So what do you want? Just Kaggle, right? Kaggle, Google data research, right? Will help you. So classification task based on image based classification, I told you, no, image based classification. So these are the model which is listed over here in histopathology images, right? Google Net, Inception, ResNet, DenseNet, Inception, ResNet, IRR, CNN, BCNet, BreastNet, MRI Net, and then here the green color. So green color, why I mark it? Because this is our lab, right? NITK. So LiverNet, LiverPoint, 2.x, Redland Net, Redland grading, RCG Net, and so on. You'll get that, right? Now, so if you visit my NITK web page, you get the recent paper, recent work, GitHub code. Not there, you just drop a mail, right? We'll provide as well, right? Now, then these are the segmentation models task, right? So if you see that these are the standard models used, deep learning models, FCN, UNet, SegNet, Deep Lab, Attention, DIST, HoverNet, OverNet, MacroNet, HMDN, HMEDN, Nucleus SegNet, SCPNet, PPNet, Kidney SegNet, DRSNet, and so on, right? Now, so again this green comes from my lab, right? Computer vision lab. And these are the like image denoising task if you want to do. These are the models are there. Autoencoder is one such. Start from there. CBDNet, PrideNet, ADNet, BRDNet, RideNet. See, we didn't work much on the denoising part, right? But there are guys who work on that, so you can refer that. And like multi-model medical fusions, autoencoder, FWNet, and these are other networks are there. You can use that as well for doing multi-model fusion. Of course, right, there is a limitation of a student, right? So we can work on the more focus in our actual task, like developing AI-based solutions for end-to-end grading for the histopathology. That's my strength, my lab strength, right? So this is a CAD system which used traditionally, right? Cancer, like before deep learning, right? We used to do image data is there. Then we do call pre-processing. Yeah. I'll finish on time. Segmentation, and then feature extraction, classification, and then cancer, non-cancer. So here everything goes step by step, right? Now, but due to the after the introduction of the deep learning architectures, right? You need not to do individual task. You can do one go task, right? Now, like feature extraction, as I told you yesterday, will happen automatically, right? So your convolution layers, pooling layer will help us to do the automatic feature extraction, right? Now, this you have seen. I'll not talk on this. Liver cancer types again are there. That's called hepatocellular carcinoma, and this called CC liver tumors. We have worked on the SCC only, hepatocellular carcinoma, right? You can read later on more about this, right? I'll provide the slides so you can read later on. This is a data set basically. If you see 4 types, because getting a liver histopathology data is very difficult, right? So we did not get a sufficient number of samples, right? All grades. So what we did, normal, grade 1, grade 2, and then higher grade, right? Higher grade basically that low, medium you can say as well. We did like normal, low, medium, and high. Basically high means upper 2, grade 3, 4 we have combined that, because we were not having the sufficient number of the sample from the KMC hospital. But you can see that the samples, right, how it looks like, different cases. And these are the characteristic cellular, characteristic changes in the hepatocellular carcinoma images, like all 4 images. I'll not skip. I'll go for that more on the architectural part. So this is very important steps, right? Building a deep learning architecture for classification of liver cancer grades, right? From the histopathology. So these are the steps. Collect data from the hospital or from the public this repository, public sources. Understanding and pre-processing of data is must. Create a deep learning model, then training of deep learning model, testing of deep learning model, performance evaluation of deep learning model, and then testing of deep learning model on new samples, right? Apart from this, you have to also go for web-based app development, right? If you do that, then you are making as a complete software product which radiologist, pathologist can use your AI solutions. If you are not doing that, it will be just end up with a paper only, right? So don't end up with a paper, try to take the next level, right? So that someone can use. And these are the implementations like Crash framework using TensorFlow library, only Crash TensorFlow framework, PyTorch framework. These are three popular which already talked about yesterday in the first lecture as well. These are the for binary classification if you do, like cancer detections, like liver cancer, non-liver cancers, right? You can use this as a binary classification model you can develop. If you're doing grading, then you have to follow these set of rules which already discussed in study class. This is something important for you, right? We have input data, patches coming, doing pre-processing, so divided into 5 folders, slides, random cropping, image resizing, normalizations. Then we have done training process, and also training we also did call 5-fold cross validations as well. And these are the models: ResNet, DenseNet, InceptionNet, and then BreastNet. Then finally model what we propose, and the classifier non-cancerous subtype 1, 2 and 3 only, right? Because of limitation of data. And then test samples, we are able to predict which particular type is there right now. And this paper was the first paper, right, in the domain was called end-to-end deep learning models, right? Data set created, and then also that train test on end-to-end basis, and after that people have followed coming that. But before that there was no paper was available. So this paper was published 2021, right? That's called LiverNet. Then this is a VG16 models. 10 minutes, okay?
We have to go somewhere else. We'll get a time on next tomorrow again.
Okay. So then we'll stop here. We'll continue tomorrow, and then I will give you one. But this part will be continuing the lab, right? So where we'll be completing this part, and then I'll demonstrate as a one model through the, at least understand some practical aspect as well, right? Now, how to develop a multi-class classification model or classifier, right? Now, okay. So we'll be discussing one as in a lab part, okay? Okay. Thank you for listening.